So now we are going to discuss the one important concept of induction machine, which is the comparison of transformer and also the induction motor. This is a very important concept. So now we are going to compare the transformer and also the induction motor. So you can see clearly this is a transformer at no load condition. At no load condition means we are not going to keep any load to the secondary winding. So this is the primary winding and this is the secondary winding. So for the primary winding we are going to give some supply voltage. So it is going to give some current of I0, because even though there is no load, still there will be a small amount of current which is taken by the primary of the transformer. So this is called as the I0, or you can say no load current. So this is the EMF induced in the primary coil, and E2 is the EMF which is induced in the secondary coil, and phi is the flux which is flowing in the transformer core. Then I want to draw the phasor diagram at the no load condition. So this is the supply voltage V. As I have already told you, the flux phi in the transformer is going to lag the supply voltage by 90 degree, and phi is produced because of the phi m. So we can say simply, or we can say for a lagging circuit, because Im is nothing but inductive part. So for inductor, current is going to lag the supply voltage by 90 degree, and Im is responsible for the flux phi. So now, then definitely there will be a current I0. So I0, if you do it to components, this is Im and Ic. So this is called as a magnetizing component, and this is called as the core loss component, and the phase angle between the supply voltage and the supply current is called as the power factor angle phi naught. So phi naught is a very huge value. At no load condition it is nearly equal to 70 to 80 degree, and the no load current is only 2 to 6% of the rated current. So we can say clearly, as phi naught is a very high, so Im is always greater than the Ic. So therefore Xm is always lesser than the Rc. So magnetizing reactance is always lesser than the Rc value, which is called as a core loss resistance. So this is the point that you always have to remember in a transformer at no load condition. Now we will do the same analysis for the induction motor at no load condition. So this is the induction motor at no load condition. So we can see clearly there is a stator and a rotor. So for stator I am going to give a supply. See, this shaft I am not going to connect to any load, so load is not there. So whenever I am not going to keep any load, so I can say the rotor speed is nearly equal to synchronous speed. So what is the value of slip? Slip is equal to ns minus nr by ns. So as nr is nearly equal to ns, so slip is nearly equal to 0 at no load condition. So slip is nearly equal to 0. See, whatever the input current taken by the stator at no load condition is called as the no load current. So I0 is a no load current which is taken by the stator at no load condition. So therefore, as it is going to take the current from the stator, it is going to produce some rotating magnetic field in the stator. So it is the rotating magnetic field is going to get produced. I have already told you two important conditions. There should be a three-phase winding, and this three-phase winding should be 120 degrees apart spatially, and we have to give supply so that the phase difference between the currents should be 120 degree between them. Then only we are going to get the RMF, rotating magnetic field. So whenever this rotating magnetic field is going to cut the rotor, an EMF is induced. It is equal to S into E2, and the rotor current which is induced in the rotor is I2 dash. All these things I have already told you. See, as a slip is nearly equal to 0, therefore we can say the induced EMF in the rotor is nearly equal to 0. So therefore now if I want to draw the phasor diagram of the induction motor at no load condition, you can see clearly this is the supply voltage V, and this is the flux phi, which is rotating magnetic field. Here flux phi is nothing but rotating magnetic field in the stator. So now if I take this current I0, so this is called as a no load current I0. See, this is the value of the current I0. So if I split it to two parts, one is called as the core loss component and other is the magnetizing component. So if you see clearly, phi naught is a very huge. It is very huge when compared to transformer, which is 80 to 85%. So we can say, and the no load current is also very huge, which is 30 to 50% of the rated current. So we can say the power factor angle is very high, and also the I0 is also very high, which is 30 to 50% of the rated current, because air gap is present. So the air gap has more reluctance, so we need more amount of current to produce the constant flux. So Im is always greater than Ic. So we can compare these two things, which is, see, in a induction motor, the value of phi is very high when compared to phi in a transformer, and also I naught is also very high when compared to transformer, and Im is also very high when compared to IC. Similarly for the comparison of transformer. So at no load condition we can say that the power factor angle of the induction motor is very high when compared to transformer. So we can say the power factor is very less of induction motor when compared to transformer, and also the no load current is very high, which is 30 to 50% of the rated current of the induction motor when compared to transformer, and also Im is also very high when compared to Im of the transformer. So this is the way that you need to compare the no load condition of the transformer and also the induction motor. So now we will analyze some more important things. So this is a transformer. So for this transformer, this is called as a primary winding and this is called as a secondary winding. So primary winding, we are going to give some supply voltage V, and because of that we are going to keep a load, we are going to connect a load to the secondary of this transformer. So as we are going to keep a secondary across the load across the secondary, the primary has a number of turns N1, secondary has a number of turns N2. E1 is the induced EMF in the primary winding and E2 is the induced EMF in the secondary. As we are going to connect the load to the secondary winding, it is going to drive current of I2 in the secondary, and I1 is the current in the primary, and phi is the flux in the core. As I have already told you, E1 by E2 is equal to N1 by N2 is equal to I2 by I2 dash. So this is a very important formula, which is I2 dash. This is not I1. This is called as the I2 dash is equal to transformation ratio, which is called as the, or we can say turns ratio, which is primary by secondary means turns ratio, which is K. So what is the value of net current? I1 is equal to no load current plus I2 dash. It is a vector sum of the no load current plus I2 dash. So then we are going to get the net current I1. Because what happens if suppose there is some air gap, suppose if I cut the core of the transformer here and also here, then what is the changes that we are going to see here? So this is the primary winding, this is the secondary winding. Primary winding has a number of turns N1 and the secondary winding has a number of turns N2. So if I assume, if I am going to connect a load to the secondary winding, the secondary winding is going to give a current of, suppose let me assume this is I2 dash. Then what is the current here? Then the current here is very simple, which is I2 dash by K. Very simple. So therefore you can apply that one. So therefore if this is I2, suppose if you think this is the current I2, then this is called as the I2 by K. See, think this is called as the I2, so this is I2 by K. So this is basically I2, then this is called as the I2 by K, because here I2 by I2 dash is equal to K, so I2 dash is equal to I2 by K. If this is I2, then this is called as the I2 by K. Or you can simply write this is I2 dash, then this will be I2 dash by K. Or you can say what is the value of K? K is the ratio of the primary winding by secondary winding. So N1 by N2 is equal to stator turns per phase by rotor turns per phase. If you try to analyze this type, this is somewhat of the induction motor. So this is N1 is called as the stator turns per phase and N2 is the rotor turns per phase, which is nothing but E1 by E2 at standstill condition. So this is called as the E1 by E2 at the standstill condition. So it is a ratio of the E1 by E2 at the standstill condition. So it is a ratio of E1 by E2 at the standstill condition. So now if I draw the phasor diagram during loading condition, what is going to happen, that we are going to see now. So this is supply voltage, this is the flux in the core, and I already told you this is the no load current, and this is the EMF induced in the secondary winding, and let me assume the load is a lagging load, so current is going to lag here. So if you take the reciprocal of this one, so if you take in the opposite direction, we are going to get, which is I2 dash is equal to I2 by K. So if you do the vector sum of these two currents, we are going to get a net current, this is called as the I1. So we can say now the power factor angle is decreased, so therefore the power factor is improved. So I1 is equal to I0 dash I0 bar plus I2 bar by K. So therefore we can say simply during loading the power factor of transformer improves, because we can say net power factor angle between the supply voltage and supply current is decreases. So we can say the power factor is improved. So during loading the power factor of the transformer is improved. So now we will see same thing that we will now analyze for the induction motor, and we will see what is going to happen. So this is the supply voltage and this is the flux in the core, which is called as the rotating magnetic field. So if I take these two things, this is called as the I0, I have already told you. Let me assume the EMF induced in the rotor is called as the S into E2, which is going to lag the flux, rotating flux, stator flux by 90 degree. So let me assume the load is a lagging load. So therefore, as basically the rotor is a R and L type, so definitely it's a lagging load. So therefore, the rotor current is going to lag the EMF induced in the rotor by small amount of angle theta. So this is I2 dash. Let me assume this is I2 dash. Then the current referred to the stator is called as I2 dash by K. So if we take the reciprocal of this one, we are going to get I2 dash by K. Now do the vector sum of these two currents, we are going to get the net current I1 in the stator. So you can see clearly the power factor angle is decreased now. So therefore, what is the net current I1 is equal to I0 bar plus I2 dash bar by K. So therefore, during loading, the power factor of induction motor is improved. So during loading, the power factor of induction motor is improved. So during loading, the power factor of induction motor is improved. So therefore, you can see as the power factor angle decreases, the power factor increases. So during loading, the power factor of induction motor is improved with the help of this process. So we can say clearly, so during loading of transformer, the input power factor is also improved. Same thing for the induction motor also. So if you go for the loading, the power factor of the induction motor is also increased. So we can say clearly, see by loading, the power factor of the transformer is increased, the power factor of the induction motor is also increased. That is the simple concept that we can learn from this intelligent concept. So therefore we can say that I have already told you the rotor equivalent circuit. The rotor equivalent, as I have already told you, the rotor equivalent side will be, I have already told the EMF induced is S into E2, and the rotor resistance is R2, and the rotor reactance is S into X2, and the rotor current is I2 dash. All these things I have already told you. The current here is I2 dash. So we can say this is the current I2 dash. So I2 dash is the current which is flowing in the rotor I2 dash. So therefore this is called as the rotor equivalent side. The theta is called as the rotor impedance angle. So theta is called as the rotor impedance angle. So this theta is called as the rotor impedance angle. So this is, if you try to find the, we can say the reactance, or we can say tan theta is equal to S into X2 by R2, we are going to get this impedance angle. So rotor impedance angle. So theta is called as a rotor impedance angle. By this, the current is going to lag the rotor induced voltage. So I2 dash, the rotor current is going to lag the rotor induced voltage by this angle. This theta is called as the rotor impedance angle. So this theta is called as the rotor impedance angle. So now we will discuss one more important thing is here, comparison of transformer and induction motor. So finally we are going to write some important points regarding the comparison of transformer and also the induction motor. So this is a transformer and this is the induction motor. So in a transformer, I have already told you the permeability is very high. The permeability of transformer core is very high. So we need less amount of magnetizing current to get the flux. So listen, in a transformer, the permeability of the core is very high. So we need less current. We need less amount of magnetizing current to produce a flux. Whereas in induction motor, there is an air gap. So we can say as the air gap is there, the permeability will decrease because the permeability of air is very less. So as permeability decreases, we need huge amount of magnetizing current to produce a given flux. And I have already told you in a transformer, at no load condition, whatever the current drawn from the input is only 2 to 6% of the rated current. Whereas in the induction motor at no load condition, the amount of current which is withdrawn from the supply is nearly 30 to 50% of the rated current, because as there is an air gap, it needs huge amount of current to produce that constant flux. The low power factor at no load in a transformer, as I have already told you, low power factor at no load, whereas in induction motor, it's a very low power factor at no load. So we can say simply at no load condition, the power factor of induction motor is very low when compared to the power factor of transformer at no load condition. So therefore, both are low, but induction motor is further low when compared to transformer at no load condition power factor. So we can say finally the power factor of induction motor at no load condition is very less when compared to transformer no load condition power factor. So the low power factor at no load and this is very low power factor at no load. So for the transformer during loading, the power factor improved, which is better than induction motor. So we can say that the power factor, so if you go for the loading of transformer, the power factor is improved. This improvement is very high when compared to induction motor. Whereas here during loading, the power factor improved, but it is lesser than the transformer. So we can say during loading, if the power factor improvement of transformer is very high when compared to loading of induction motor improvement of power factor. So we can say if you load the transformer and the induction motor, the improvement of power factor in the transformer is quite very high when compared to the induction motor power factor. And the primary and the secondary has same frequency. So in a transformer, whatever the frequency in the primary winding will have the same frequency in the secondary winding, whereas it is quite different. So stator winding has a frequency F and the rotor has a S into F. I've already told you stator winding will have a frequency F, whereas the rotor winding will have frequency which is S into F. So both are different frequencies. We never practically short circuit the transformer. See, we never practically short circuit the transformer. See, always we keep the load at the end of the transformer, but we never prefer to short circuit the transformer because we use transformer for loading purpose, not for short circuiting. So short circuiting the transformer is not our important agenda. We always keep the load at the end of the transformer. So we never practically short circuit the transformer, but always rotor is short circuiting. So in the induction motor, the rotor is always short circuited, or you can say secondary is always short circuited. Whereas in a transformer, we always keep the load. We never practically do the short circuit. Whereas here, always the rotor is short circuited. So we never practically short circuit the transformer, whereas always the rotor is short circuited. And here we are going the transformer, whatever the load is called as the electrical load. Whereas here we are going to keep a mechanical load. Or simply we can say no electrical load. For a transformer, we keep the electrical load. For induction motor, we are not going to keep an electrical load, or simply we can say we are going to keep a mechanical load. And the turns ratio govern the induced voltages. So turns ratio is going to tell you how much amount of induced voltage in the secondary if you know the induced voltage in the primary. Whereas turns ratio govern induced voltages only at standstill, but in running it depends upon slip. So we can say whatever the induced voltage in the secondary, or we can say in the rotor, we can figure out only at the standstill condition, while at running we can only figure out with the help of the slip. So turns ratio govern the induced voltage only at standstill, but in running condition it depends upon the slip. So only during the standstill condition we can figure out the EMF induced in the rotor with the help of the turns ratio, whereas during the running condition there is an extra factor of slip we are going to get in the induced voltage, which is S into P2. So we can say turns ratio govern the induced voltage only at the standstill, but in the running condition it is going to depend upon the slip. And in the transformer we are going to use the constant rigid winding. So in the transformer we are going to use the concentrated winding, whereas in the induction motor we are going to use the distributed winding. So in the transformer we are going to use the concentrated winding, whereas in the induction motor we are going to use the distributed winding. And in the transformer, leakage reactance is very less because the leakage flux is very less, so therefore the leakage reactance is very less. Whereas in the induction motor, the leakage flux is very high, so therefore more leakage reactance. So therefore we can say that in a transformer the amount of leakage flux is very less, so therefore the leakage reactance is less. Whereas in the induction motor, the leakage flux is very high, so therefore we are going to get the more leakage reactance. And basically the transformer is basically a constant flux machine, whereas the induction motor is also a constant flux machine. So these are some of the important comparisons of the transformer and also the induction motor. So let me do a quick review of the transformer and induction, the comparison in a very speed manner. So the transformer, the permeability of the core is very high, so we need less amount of magnetizing current to get the constant flux. Whereas in induction motor, as there is a air, so therefore the permeability is very less, so we need huge amount of magnetizing current to produce a constant flux. At no load condition, whatever the current drawn by the transformer, this called the no load current, it is nearly 2 to 6% of the rated current. Whereas in the induction motor at the no load condition, the current drawn from the supply is 30 to 50% of the rated current. It is very high when compared to this one. At no load condition of the transformer and induction motor, the power factor is very less, but the power at no load condition, the induction motor has very less power factor when compared to transformer. And during loading condition, the power factor improvement in transformer is quite very high when compared to improvement of power factor in induction motor. Or we can say the improvement of power factor in transformer at loading condition is very high when compared to improvement of power factor at loading condition of induction motor. So in the transformer, the primary and the secondary has the same frequencies. So primary winding and secondary winding has the same frequency, but in the induction motor, the primary or the stator has a frequency F and the rotor has a frequency S into F. So transformer, we always try to keep the load at the secondary of the transformer. So we never go for the short circuit of transformer, but the rotor of the induction motor is always short circuit. So for transformer, we always keep the electrical load, whereas for induction motor, we never keep electrical load, or simply we keep a mechanical load. So in the transformer, turns ratio is going to govern the induced voltages. So if you know the turns ratio and if you know the induced voltage in the primary, we can get the induced voltage in the secondary at any condition. Whereas here, the turns ratio is going to govern the induced voltages only at the standstill, but in running, it depends upon the slip. So if see, this turns ratio is going to give you the amount of EMF induced in the rotor only at the standstill condition, but during running condition there is an extra factor of slip, yes, so S into E2. In transformer we prefer to use the concentrated winding, whereas in the induction motor we prefer to use the distributed winding. And in the transformer the leakage flux is very less, so leakage reactance is also less, whereas in the induction motor the leakage flux is very more, so therefore the leakage reactance is also very more. And the transformer is a constant flux machine, and the induction motor is also a constant flux machine. So now we'll discuss some important concepts which is called as the equivalent circuit representation of the induction motor. So now we are going to actually provide an equivalent circuit of the induction motor. So now we will see something about this one. See, this diagram is same as the transformer diagram. Supply voltage, this is the R1, X1, primary winding, resistance and reactance. This is a per phase diagram. So R1, X1, and this is the we can say the core, we can say this is the core loss resistance and the core loss reactance, and this is called as the rotor circuit. So this is the stator circuit and this is the rotor circuit per phase diagram. See R1, X1, this is RC and this is XM, and this is IC and this is IM and this is I0. So this is the secondary winding. If the EMF induced here it is suppose, so here it will be suppose if it is even, here means here it is S into E2, EMF induced in the rotor, and this is R2 and this is the S into X2. I have already told this one. This is S into E2, this is R2 and SX2, and the current here is I2 dash. So if you know the turns ratio N1 N2, so N1 by N2, so N1 by N2 is nothing but K. So therefore here you are going to get I2 dash by K, because I have already told you, see this current by this current is equal to, see this current by this current is equal to this current, this turns by this turns, this is called as a K. So this is N1 by N2 is equal to K. So therefore this current is I2 dash means this current is I2 dash by K. These things I have already told you. So therefore now I have already told you IM is very very high in an induction motor. So IM is very 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 high when compared to IC. So reverse is nothing but XM is always lesser than the RC. Current is very high means the reactance part is also very less. So XM is very very less when compared to RC. So this is the, we can say this part is similar to a transformer, but only thing is here we have to always do the short circuiting of the rotor. Only this is the point that you always have to be very careful. So now what is the value of I2 dash? I2 dash is equal to EMF by total reactance. So I2 dash is equal to S into V2 by total impedance is equal to R2 plus J into SX2 is equal to, so do the division by S on numerator and denominator, we are going to get E2 by R2 by S plus J into X2. So if I do the ratio of S on the numerator and denominator, I am going to get in this fashion, which is E2 by R2 by S plus J into X2. Then I will try to represent in this format. So this is same as the previous one. Supply voltage R1, X1, RC, XM, IC, IM, I0, I2 dash by K, and this is the E2, and now this is called as the E2, and this is the X2, and this is the R2 by S, because here S is nothing but slip. So whenever the load is varying, S is varies, so this overall value is also varying. That is the reason we are going to keep a variable resistance in this format. And further now we will do some more simplification. So same thing, this primary is the same as this one. Supply voltage R1, X1, RC, XM, IC, IM, I0, I2 dash by K. And see, this is the same as this one, but only thing is here, we are going to add some more extra K. So this is E2, this is I2 dash, this is R2, X2, here R2 into 1 by S minus 1. So if you do the resistance addition, see R2 by S minus R2 plus R2 is again same thing R2 by S. So therefore extra thing that we are going to have here minus 1. So therefore we are going to get R2. So this circuit and this circuit is still the same circuit, but the only thing is here we did some manipulations. That is the only thing that we have did here. So therefore add minus R2 here plus R2 here. So same thing we are going to get. So this is called as the RL. So therefore this as S changes, this whole value changes. That is the reason we are going to keep an extra arrow, or you can say variable resistance. It is an electrical equivalent of mechanical load. So whenever the load is changes, so this is called as the electrical equivalent of a mechanical load. As the mechanical load changes, S changes, its overall value changes. So we can say simply this is called as the electrical equivalent of a mechanical load. So this is called as electrical equivalent of a mechanical load. So now you can see clearly this is same as a transformer, same thing as a transformer, but only thing is here we are going to keep a load which is electrical load which is equal to a mechanical load. Electrical equivalent of mechanical load, its load value RL is equal to R2 into 1 by S minus 1, where R2 is the rotor resistance, S is the slip, and remaining everything is same as that of a transformer. Supply voltage R1, X1, RC, XM, IC, IM, I0, I2 dash by K, this is I2 dash, this is E2, R2, X2, and this is called as a, we can say, electrical equivalent of mechanical load. So same thing exact transformer, this is called as the electrical equivalent of a mechanical load. So now what we are going to do, what is the rotor at starting condition? So this is only thing that we are going to see only the rotor part at the starting condition. At starting condition I have already told you what is the value of S. At starting condition NR is equal to NS. So therefore at starting condition NR is equal to NS. So we can say clearly whenever the NR is equal to NS, slip is equal to 0. Okay. At the starting condition always the rotor is not at all started. So NR is equal to 0. So slip is equal to 1. So if we keep slip is equal to 1, 1 minus 1 is nothing but 0. So therefore this is the short circuit. At starting condition rotor speed is equal to 0. So slip is equal to 1. So if we substitute here 1, this is nothing but 0. So short circuit. So therefore E2, R2, X2, I2 dash. Here we have to keep here. So we can keep here I2 or I2 dash. Everything is same. So this is called as frequency F, because as S is equal to 1, here stator frequency is equal to rotor frequency. So therefore this is also frequency F. And now we will see at the running condition. So now at running condition what is going to happen. So at running condition I have already told you, see at running condition I have already told you very important point, which is called as the same thing. If you see, you can draw this circuit or you can draw this circuit, both are very same. So you can draw either this circuit or either you can keep this circuit. Same circuit you can draw, redraw, or you can skip in the another form, which is S into E2, R2 into SX2, this is the I2 dash. So rotor at the running condition. You can use either this one or for the starting condition, and this is for the running condition, and the rotor frequency is equal to S into supply frequency. So now if I bring the rotor to stator, so everything if I bring to stator, then what is the equivalent circuit diagram that we are going to see. So this is the supply voltage, this is R1, X1, RC, XM, this is called as the IC, this is the IM, and this is the I0, everything is same. But now we are going to shift from the rotor to stator. So here R2 will become R2 dash, X2 will become X2 dash, and this will become R dash into 1 by S minus 1 is equal to Rn dash. Just we have to change it or scale it by N1 by N2 whole square. So therefore R2 dash is nothing but R2 dash is equal to N1 by N2 whole square into R2, and X2 dash is equal to N1 by N2 whole square into X2, and R2 dash is nothing but R2 into N1 by N2 whole square into R2. So therefore like this you can write. So with respect to stator, so therefore I have already told you K is nothing but N1 by N2. These things I have already told you, K is nothing but N1 by N2. So therefore R dash is equal to N1 by N2 whole square into R2, and X2 dash is equal to N1 by N2 whole square into X2, and we can say that this is the thing. So K is always N1 by N2. So now this is called as a stator input. So this arrow indicates that this is stator input, and this is called as the, and this is up to stator, but this is the rotor. So this is called as the air gap power, or we can say rotor input. So this is called as a air gap power or rotor input. This is the circuit diagram with respect to stator. So this is the equivalent circuit diagram of induction motor with respect to stator. So this is the point that you always have to remember. This is the supply voltage R1, X1, RC, XM, R2 dash, X2 dash, and this is R2 dash into 1 by S minus 1 is equal to R dash with respect to stator. This is the stator input, and this is the air gap power or rotor input. So let me assume the current here is I1. So let me assume the current here is I1. So I1 square into R1 is called as the stator copper loss. So I1 square into R1 is called as the stator copper loss. So I1 square into R1 is called the stator copper loss. And this is IC square into RC is called the stator core loss. So I1 square into R1 is called as the stator copper loss, and IC square into RC is called the stator core loss. Here it is I1, here it is IC. So I1 square into R1 is called the stator copper loss, and IC square into RC is called as the stator core loss. So stator input minus stator loss. So stator input minus stator loss is nothing but stator output, a rotor input or air gap power. And what I told you, stator input minus stator loss. Stator loss is a combination of the stator copper loss and stator core loss. Then we are going to get rotor input, or you can say stator output or air gap power. So stator input minus stator loss. So stator loss is a summation of the stator copper loss and stator core loss. We are going to get stator output, rotor input or air gap power. So this is a point that you always have to remember. Stator input minus stator loss. Stator loss is a combination of stator copper loss and stator core loss. We are going to get stator output, rotor input or air gap power. So this is the IEEE notation, standard representation of induction motor. So here this is called as the R1 X1, R2 dash X2 dash, RL dash is equal to R dash into 1 s minus 1, then XM. So here we are going to remove the RC, because I have already told you RC is a very huge value when compared to XM. So we are going to neglect it because it's a very huge value. So we are going to neglect it. In a parallel combination, the overall value will be equal to minimum value. So it is a huge value, we can remove it. So this is called as IEEE standard representation. So now approximate equivalent circuit. Just bring this one here and bring this part to the here. So you are going to get a equivalent circuit. So this is called as the I2 dash. So therefore here R1 plus R2 dash, X1 plus X2 dash, and RL dash is equal to R2 dash into 1 by S minus 1. This is a variable resistor. So it is a variable resistor. Here also you have to keep a arrow. So here also you have to keep a variable arrow. So therefore just to bring this one, keep it here. So you are going to get like this. So this is the per phase diagram. So approximate equivalent circuit. So V phase, there XM, R1 plus R2 dash, X1 plus X2 dash. This is I2 dash current, and this is RL dash is equal to R dash into 1 by S minus 1. So we can say this is the equivalent circuit or approximate equivalent circuit of an induction motor. So now some important points here. So what is the torque expression? I have already told you, cross torque or mechanical power developed is equal to 3 into 60 by 2 pi ns into, I have already told you, the rotor input is nothing but, rotor input is called as the rotor copper loss by S. So rotor copper loss. So rotor copper loss, if you want rotor copper loss, it's very simple, which is I2 dash magnitude part whole square into R2 dash by S. So I have already told you rotor copper loss. So rotor copper loss, what is the rotor copper loss? See, listen carefully. One point I have already missed here. So very point. So what is the value of torque? See, R is equal to torque into omega. So what is the torque? Torque is equal to power by omega. So here rotor input power. Rotor input power is nothing but copper loss by rotor copper loss by S. Rotor copper loss 3 into. So 3 into magnitude of I2 dash whole square into R2 dash by S. Rotor copper loss by S. So rotor copper loss is 3 into for 3 phase winding. So therefore 3 into magnitude of I2 dash whole square into R2 dash. So magnitude of I2 dash whole square into R2 dash. So therefore by S. So this is 3 into here by P is equal to T into omega. So T is equal to P by omega. Omega is nothing but 2 pi ns by 16. So 60 goes upward. So finally after rearranging we are going to get 3 into 60 by 2 pi ns into magnitude of I2 dash whole square into R2 dash by S. So this the current here is I2 dash. So I2 dash whole square into R2 dash, or we can say per loss copper. So we can say per phase rotor copper loss. So per phase rotor copper loss. So per phase rotor copper loss, I2 dash magnitude whole square into R2 dash is called as the per phase copper loss. So per phase rotor copper loss. So I2 dash magnitude whole square into R2 dash is called as a per phase rotor copper loss. So during starting, what is going to happen? During starting, the rotor speed is equal to 0. So S is equal to 1. So whatever the torque we are going to get, it's called as the starting torque. Then what is the value of RL dash? RL dash is equal to R2 dash into 1 by S minus 1. As S is equal to 1, the overall value is equal to 0. So this, if you keep here, the starting expression 3 into 60 by 2 pi ns into, so now this is as s is equal to 1 here. So what is the value of I2 dash? I2 dash is nothing but V phase. So V phase by R1 plus R2 dash whole square plus X1 plus X2 dash whole square. So therefore again under root just take the square of that. So we are going to get this current. So what is the value of I2? Suppose if this is a circuit, then what is I2 dash? At starting this x is equal to 1, this value will become 0. So I2 dash is equal to V phase by R1 plus R2 dash plus J into X1 plus X2. But I want magnitude value. So therefore V phase by under root over R1 plus R2 dash whole square plus X1 plus X2 dash whole square. But if I want the I2 dash whole square, it's V phase whole square by R1 plus R2 dash whole square plus X1 plus X2 dash whole square. So we can substitute here into R2 dash. So therefore this is called as the basically this is called as the starting torque expression. So 3 into 60 by 2 pi ns into as s is equal to 1 here. So magnitude of I2 dash whole square into R2 dash. So this is the part you are going to get here. As I already told you, the magnitude of I2 dash is nothing but V phase by under root over R1 plus R dash whole square plus X1 plus X2 dash whole square. I have already told this one from the approximate equivalent circuit. So now we are going to discuss one more important concept of induction motor, which is called as the no load test on induction motor. So now we discuss the no load test on the induction motor. So basically we are going to perform the no load test on induction motor. So this is basically induction motor of stator, and this is the rotor, and this is the shaft of the rotor. So now the stator we are going to give 3-phase supply. So this is a 3 windings. So we are going to give a balanced 3-phase supply. So this is the voltmeter we are going to keep. So this is the line voltage. It is called as the no load voltage, or we can say the line voltage, or simply the no load voltage. And the current drawn at no load is called as the no load current. So this is the no load voltage, and this is the no load current. Basically this is called as the line voltage, and this is the no load current. Here we are going to keep the ammeter to measure this current and the voltmeter to measure this line voltage. And here we are going to keep 2 wattmeters. So here we are going to use the 2 wattmeters method to measure how much amount of power is drawn by this stator to consume, how much amount of power is consumed by this induction motor we are going to figure out. So by using these 2 wattmeters, W1 and W2. And you can see clearly here at no load, and you can say we are not going to keep any load. So definitely NR is nearly equal to NS. So slip is nearly equal to 0. So therefore because rotor speed is nearly equal to synchronous speed at no load condition. So with this now we will move forward to analyze each and everything in this no load test of induction motor. So what is the no load losses? So at this no load, the amount of power drawn by this circuit, by this induction motor is called as the, which is W1 plus W2. So W1 plus W2. See, there is no useful work, there is no useful power is done. So definitely this power is wasted in terms of losses. So whatever the power which is taken, it is losses in this motor because there is no useful work done, or no useful power is used. So therefore the no load power, the total power consumed by this induction motor at this no load condition is W1 plus W2 is equal to losses, because there is no useful work done. So whatever the power taken, it is used for the losses. So whatever the input power is basically output plus losses, as there is no useful work done. So output power is equal to 0. So whatever the input power should be equal to losses. So what are the losses in the induction motor? I have already told you: stator copper loss, stator core loss, rotor copper loss, and rotor core loss, and mechanical losses or windage losses. All these things I have already told you. In the stator there are 2 losses: stator core loss and stator copper loss. In rotor there are 2 losses: rotor copper loss and rotor core loss. And we are going to get mechanical losses, means basically windage and friction. So all these things we are going to include in one thing, which is called as the mechanical losses. I have already told you rotor core loss is very less, so we are going to neglect it. See, at no load condition, the amount of current drawn in the rotor is also very less, because slip itself is very less. As slip itself is equal to 0, so induced voltage is also 0, as the induced voltage in the rotor is equal to 0, because S into V2, as S is nearly equal to 0, so induced voltage in the rotor is also 0. So therefore the rotor current is also 0, so therefore the rotor copper loss is also 0. So we are going to neglect the rotor copper loss and also the rotor core loss. The remaining losses are called as the stator copper loss, stator core loss, and the mechanical losses. So whatever the input power is consumed in these three losses, it is called as the stator copper loss, stator core loss, and also the mechanical losses. Always stator core loss and the mechanical loss are said to be constant losses. So constant losses means it is a summation of the stator core loss and the mechanical loss are always constant for a given amount of fixed voltage. So therefore stator core loss and the mechanical losses are always said to be constant losses. So whatever the input power minus stator copper loss is equal to stator core loss plus mechanical loss is said to be constant loss. So therefore whatever the total input power minus stator copper loss is called as the constant losses. So constant losses means summation of stator core loss and mechanical loss. So WNL minus stator copper loss means basically there are 3 winding. So therefore 3 into INL square into R1. So therefore we are going to get, this is called as the constant losses. So with the help of these things we can figure out the constant losses of this induction motor. So WNL minus 3 into INL square into R1, we are going to get the constant losses of the induction motor. So if you know this thing, it is very useful to figure out the efficiency of the induction motor also. So now I will draw the phasor, or you can say equivalent circuit diagram of this induction motor. With respect to stator, I have already told you this is R1, X1, this is Xm, because RC is very huge value, so we are going to neglect it. This is R2 dash, X2 dash, and RL dash is equal to RL dash into 1 by S minus 1. As I have already told you, slip is nearly equal to 0, so 1 by 0 is nothing but infinity. Infinity minus 1 is again infinity, so therefore this value is equal to infinity, means it's a open circuit. So we are going to do the open circuit of this one. So now this is a per phase, so this is called as a per phase diagram, but per phase means the line voltage we know, which is called as the VNL. So we try to always with the stator, we always try to make the stator in a star connection. So line voltage is equal to root 3 into phase, so phase voltage is equal to line by root 3. So VNL by root 3, because VNL itself is the line voltage, so line voltage by root 3, because it is a per phase diagram. So VNL by root 3, and this is the INL. So INL and R1 I have already told you. So stator copper loss is equal to 3 into INL square into R1. So therefore this is called as the INL. So now what is the XNL? XNL is nothing but just do the addition of these two things, X1 plus XM, and RNL is nothing but R1. It is always AC because AC currents flows through the windings of stator, so it is a AC. So what is ZNL, which is VNL by root 3 by INL, so we are going to get ZNL. And what is WNL? L is nothing but, I have already told you. So WNL is nothing but whatever the input power is always offset by resistor, so therefore WNL is equal to 3 into INL square into RNL. So therefore, see RNL is nothing but R1 AC. So therefore WNL is equal to 3 into INL square into RNL. RNL is equal to basically R1 into AC. So what is RNL? WNL by 3 into INL square. Then what is XNL? XNL is equal to under root of ZNL whole square minus RNL square. So with the help of this, we can figure out one important point, RNL and XNL, because we know what is the value of WNL with the help of two wattmeters, which is W1 plus W2, and also we know INL with the help of the ammeter. So if by this we can get the ZNL, and WNL value we know, INL value we know, we can get the RNL. So if we know ZNL and RNL, we can get the XNL also, which is under root of ZNL square minus RNL square. So if you know XNL, we can easily get the X1 and XM. And if you know RNL, it is nothing but R1 AC. All these things we can figure out. So we can figure out the X1, XM and R1. All these things we can easily figure out with the help of this no load test. So with the help of this no load test, we can figure out the R1, X1 and XM. So therefore, we can say simply ZNL is equal to VNL by root 3 by INL, and WNL is equal to 3 into INL square into RNL, and RNL is equal to WNL by 3 into INL square, and XNL is equal to under root over ZNL whole square minus RNL square, and RNL is equal to R1 into AC. It is like R1 in AC format, and XNL is equal to X1 plus XM. If you see clearly, this is basically an approximate circuit. So this is approximate circuit means here we are neglecting the stator core loss. Here we are going to neglect the stator core loss. So we have assumed that stator core loss is 0, because that is why we have removed this RC component. So therefore, this is the approximation only. This is the approximation only. So this is a very approximate circuit only. So this is the point that you always have to remember. There will be some stator core loss also, but we have removed it by the help of approximation only. So we can get the R1, X1 and Xm. So now we will perform the DC test on the induction motor of stator winding. So I have already told you, stator winding we are going to connect in a star fashion. So for a single phase, we take supply voltage of V, and we keep an ammeter and a voltmeter here. And now I will try to find what is the value of R1. So at steady state condition, the inductance will be 0 because frequency is 0, its reactance will be 0. So therefore, R1 in DC format is equal to V by I. So V value we can get with the help of voltmeter, and I value we can get with the help of ammeter. So the DC value of this resistance we are going to get. But we need AC resistance, so therefore 1.5 times the R1 DC, because AC resistance is always greater than the DC resistance by factor of 1.5. So therefore we can say, we can easily get the value of the AC resistance also, which is R1 AC. Well, by performing the DC test of induction motor, we can get the AC resistance of the stator winding, which is R1 AC is equal to 1.5 into R1 DC, and R1 DC is equal to V by I. So now we are going to perform the blocked rotor test on induction motor. So we are going to perform the blocked rotor test on the induction motor. Or simply we can say it's like we are blocking the rotor. We are blocking the rotor means with forcefully we are blocking this rotor to move. So its speed is equal to 0. As NR is equal to 0, then definitely S is equal to 1 because it's a locked. So therefore slip is equal to 1. I have already told you torque is equal to power into omega. So torque is equal to, power is equal to torque into omega. So power is equal to, power is equal to torque into omega. So power is equal to torque into omega. So 2 pi n by 60 into T, because omega is equal to 2 pi rotor speed. Because shaft power we have, shaft power means we have to use the rotor speed in the radians per second. So PH is equal to omega 2 pi n by 60 into T. As the rotor speed itself is equal to 0, so this power is equal to 0. So shaft power is equal to 0 because no useful work is done. So whatever the input power should be used in terms of losses. So blocked rotor test or induction motor. So shaft power is equal to 0 because the rotor speed itself is equal to 0. So shaft power is equal to 0. So we are going to give some 3-phase balance supply to the stator winding. So these are the 3 phases. We are going to give this 3-phase balance supply. So this is a voltmeter and this is the ammeter. So we are going to use the two wattmeter method to measure the how much amount of active power which is consumed by this induction motor at this test. So this is called as we need only 10% of rated voltage, very less amount of rated voltage only we need, which is 10% of rated voltage. It is required to produce a rated current in the stator. So we can say that whatever the rotor voltage at this condition, we need a very less amount of voltage, which is around 10% of the rated voltage to produce a rated current in the stator. So this I rated is called as a block rotor current, or you can say this VBR is equal to 10% of rated voltage. Means during this we need a very low amount of voltage to get the rated current. That voltage is nearly 10% of rated voltage, and this is the rated current is equal to IBR. So whatever the power consumed at this condition is called as the W1 plus W2. So this is called as the power consumed in this block rotor test is equal to W1 plus W2. I have already told you, as the speed itself is equal to 0, so mechanical loss is also 0. So mechanical loss is 0 because speed is equal to 0. See, whenever the friction and image will occur only when it is moving, as it is not at all moving, so definitely mechanical losses are also 0 because the speed itself is equal to 0. Mechanical losses means friction losses. The friction will act only when it is moving, so mechanical losses are 0 because speed is 0. So output power is also 0. Definitely the input power should be wasted in terms of losses, and we will see core loss negative because only 10% of rated voltage. See, we are going to give a less amount of voltage. See, as the voltage itself is less, so the core loss is also less. As the voltage increases, the core loss increases. As the voltage decreases, the core loss decreases. So we can say that core loss is negative because only 10% of voltage is given. So only 10% of rated voltage is given, so we can easily neglect the core loss. So core loss we are going to neglect because only 10% of rated voltage we are going to give. And now we will see the output is equal to input plus losses. So input is equal to output plus losses. As output is equal to 0, so input should be equal to losses. So I've already told you input is equal to losses. So input is equal to, what are the losses? Stator copper loss, stator core loss, rotor copper loss, rotor core loss, and mechanical losses. I have already told you mechanical loss are 0. So it is 0. And the stator core loss and the rotor core loss are neglected, because I have already told you the voltage is very less, so they are neglected. The only thing which is mechanical loss are also 0, because speed itself is equal to 0, so that is also neglected. Only two losses are there, which is called as the stator copper loss and rotor copper loss. So whatever the input power, it is consumed by only two things, which is called as the stator copper loss and rotor copper loss. So listen carefully. Input is equal to output plus losses. As the output is equal to 0, so input should be equal to losses. So losses are stator copper loss, stator core loss, rotor copper loss, rotor core loss, and mechanical losses. As mechanical losses are 0, because speed itself is equal to 0, so it is gone. The remaining things are stator core loss and rotor core loss. They are very less, because the voltage given is very less, so they are also 0. The remaining only loss are the stator copper loss and rotor copper loss. So whatever the input should be consumed by only the stator copper loss and rotor copper loss. So now we will analyze something regarding this one. So now we are going to take the approximate circuit, which is R1, X1, R2 dash, X2 dash, Xm. As RC is very high, we are going to neglect it. So what is RL dash is equal to R2 dash into 1 by S minus 1. As S is equal to 1, so RL dash is equal to 0, so therefore short circuit. So now we can say this is, see, no load test is basically like open circuit, and block rotor test is basically like a short circuit. So you can see clearly no load test is basically like the open circuit test, and the block rotor test is basically like a short circuit test. So you can do like analysis you can do similar analysis with respect to transformer. So now I have already told you this is a per phase diagram. I have already told you stator will be always cut in the stator in a star connection. So therefore this is a per phase diagram. So the line voltage by √3, because line voltage is equal to √3 into phase. So phase is equal to line by √3. So line voltage is VBR by √3, and this is a current IBR. So this is a approximate circuit, and now we will analyze one thing. So what is the ZBR? So ZBR is equal to VBR by √3 by IBR, which is equal to just to all the required analysis, which is R1 plus JX1 plus just to the parallel combination of these two things, which we are going to get finally in this fashion: J into Xm into R2 dash whole square minus J into R dash Xm plus X2 dash into X2m by R2 dash whole square plus X2m whole square, just to the parallel combination. This is series and this is the overall parallel. If you do, we are going to get this one. Here X2m is nothing but X2 dash plus Xm. It is a very huge value, because Xm is a huge value. So therefore this value is a very huge value. So therefore finally, if you do the real part and the imaginary part, finally we are going to get ZBR is equal to RBR plus JXBR. So XBR, we are going to approximate it nearly equal to X1 plus X2 dash. So we are going to approximate this XBR is nearly equal to X1 plus X2 dash. So XBR we are going to approximate nearly to X1 plus X2 dash. So X1 is nearly equal to X2 dash is nearly equal to XBR by 2. So we are going to assume both are equal. So X1 is nearly equal to X2 dash is nearly equal to XBR by 2. Then what is RBR? RBR, if you take the real part, we are going to get finally R1 plus R2 dash Xm square plus R dash whole square plus X2m whole square. Then what is the value of R2 dash? So from this I want to find what is R2 dash. So if we do the further analysis, you are going to get, see, X2m I have already told you, X2 dash plus X2m Xm. If you substitute here, X2m is equal to X2 dash plus Xm. If you substitute here, and if you do the further analysis, we are going to get R dash is equal to RBR minus R1 into X2 dash plus Xm by Xm whole square. So this is the analysis we are going to get finally. So we can get the R2 dash and also the X2 dash. So with the help of block rotor test, we can get the R2 dash and the X2 dash. So listen carefully, we can get the value of R dash and X2 dash. With the help of no load test, we can get the value of R1, X1 and Xm. Whereas with the help of the block rotor test, we can get the value of R2 dash and the X2 dash. So this is the point that you always have to remember. So with the help of no load test, we can get the value of the R1 and X1 and also Xm. With the help of block rotor test, we can get the value of the R2 dash and X2 dash. So we know the R2 dash and X2 dash is nearly equal to XBR by 2. So from block to the test meters, so ZBR is equal to VBR by root 3 by IBR. So if we know VBR, we know IBR. So if you do this one, we are going to get ZBR. Then what is the WBR? WBR is equal to 3 into IBR whole square into RBR. So therefore WBR is equal to 3 into IBR whole square into RBR. So RBR is equal to WBR by 3 into IB square. So we know WBR, we know IBR. So if we substitute, we are going to get RBR. Then XBR is equal to under root over ZBR whole square minus RBR whole square. So we can get the value of ZBR, RBR and XBR. So if we know XBR and RBR, we can easily get the value of X2 dash and also the R2 dash. So we can get the value of R1, X1 with the help of no load test on the induction motor. So listen carefully. With the help of no load test on the induction motor, we can get the value of R1, X1 and Xm. And with the help of this block rotor test, we can get the value of R2 dash and the X2 dash. So this is the point that you always have to remember for your lifetime. So with the help of no load test, we can get the value of R1, X1 and Xm. And with the help of block rotor test, we can get the value of R2 dash and X2 dash. So listen carefully. Finally, I am repeating it. So with the help of no load test, we can get the value of R1, X1 and Xm. And with the help of block rotor test, we can get the value of R2 dash, X2 dash. So now we are going to discuss one more important concept which is very much useful. Separation of mechanical and iron losses in an induction motor. I have already told you mechanical losses and iron losses both are called as the constant losses. So mechanical losses and iron losses are always said to be constant losses. The summation is called as the constant losses. But now we are going to separate this mechanical losses and the iron losses in an induction motor. We are going to study how we are going to separate this mechanical loss and the iron losses, because the summation is called as the constant losses. So we are going to perform the no load test. No load test is basically like a open circuit test in a transformer. So these things I have already told you. So open circuit test in a transformer is nearly equal to no load test in an induction motor, and a short circuit test in a transformer is nearly equal to block rotor test in an induction motor. So here we are going to keep the no load test. So at no load test is basically we can say that the speed is nearly equal to NR. So therefore we can say speed is nearly equal to NR, means slip is nothing but which is equal to 0. So slip is equal to 0. So for various voltages, I have already told you. So N is nearly equal to constant for various voltages. Even if we further increase the voltage also, we can get the speed is nearly equal to constant for various voltages. So I have already told you the 3-phase supply we are going to give here, and this is a 3-phase winding to the stator. So we are going to use the 2 wattmeters to measure the amount of active power flown from to this induction motor. How much amount of active power consumed by this induction motor we can easily figure out, W1 and W2. So what is the overall power which is called W1 plus W2? This much amount of power is consumed by the stator, and this is an ammeter, and the current is INL we can measure, and with the help of this voltmeter we can measure this voltage, no load voltage, and this is the no load current we can measure, and how much amount of power which is consumed by this induction motor at no load condition also we can measure with the help of this 2 wattmeter method. I have already told you, as we are not going to do any useful work, so definitely output power should be equal to 0. So input is equal to output plus losses, as output is equal to 0, input should be equal to losses. So what are the losses we are going to get? I have already told you the losses are stator core loss, stator copper loss, rotor core loss, rotor copper loss and mechanical losses. As you can see clearly, the rotor core loss are neglected. So rotor core loss are always neglected. And also the rotor copper loss, I have already told you slip is nearly equal to 0. So whenever the slip is nearly equal to 0, rotor EMF induced voltage is also 0. So definitely the rotor current is also 0. So the rotor copper loss is also neglected. So only thing that we are going to get is called as the stator core loss, stator copper loss and the mechanical losses. So I have already told you one important point. Stator core loss and the mechanical loss are said to be constant losses. So therefore, finally we can say input is equal to constant losses plus stator copper losses. These things I have already told in the no load test itself. So now we will further go through this one. So even if you increase the voltage or decrease the voltage to a certain range, the speed is nearly equal to constant for various voltages. So performing no load test at the various voltages, now we are going to see what is going to happen. So this is the no load voltage we are going to give, or simply we can say line voltage. See, this is the 120% of rated value, and this is the 100% of the rated value, 80% of the rated value, 60% of the rated value, and 40% of rated value. I am going to assume the speed is almost constant. It will never change. N1, 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 and N1. Because speed is going to depend upon the frequency, not on the voltage. So therefore, frequency is still the same. The speed is also still the same. So now we will see how much amount of no load current which is drawn by this stator. This is for the first case INL1, INL2, INL3, INL4 and INL5. And the input power which is taken by this induction motor at these different cases. Let me assume this is WNL1, WNL2, WNL3, WNL4 and WNL5. I have already told you the constant losses. PC is called as the constant losses. I have already told you total input power is equal to constant losses plus copper losses in the stator. So what is the constant losses? Total input power minus stator copper losses. So total input power minus stator copper loss in a 3-phase. So 3 into INL square into R1 for the first case. So PC2 is equal to WNL2 minus 3 into INL2 whole square into R1. PC3 is equal to WNL3 minus 3 into INL3 whole square into R1. And PC4 is equal to WNL4 minus 3 into INL4 whole square into R1. And PC5 is equal to WNL5 minus 3 into INL square into R1. So this is the constant losses in a machine we can easily obtain for different types of voltages. So PC1, PC2, PC3, PC4 and PC5. So total input power minus stator copper losses. We are going to get the constant losses. So this is the thing that we are going to get. As you can see clearly, INL decreases from up to down, because as the supply voltage decreases, the supply current is also decreases. So therefore, INL decreases from up to down, and the WNL decreases from up to down, because as the supply voltage decreases, supply current decreases, so overall input power is also decreases. So therefore, we can see clearly, as the supply voltage decreases, the supply current decreases, so overall input power is also decreases. As the supply voltage decreases, the supply current decreases, so overall input power is also decreases. And now we will draw the graph between the constant losses and the different things. So now we are going to draw the graph between the copper losses and the with respect to voltage. So with respect to voltage and the with respect to constant losses and the voltage, we are going to draw the graph. So this is for 120%, 100%, 80%, 60% and 40%. As you go in this direction, as you decrease the voltage, so you can say clearly, as you decrease the voltage, the line current decreases. As the line current decreases, the overall input power decreases. As the overall input power decreases, the constant losses also decreases. So listen carefully. As the supply voltage decreases, the input current decreases, the input power decreases. So therefore, the constant losses also decreases. So therefore, the constant losses are going to decrease in this manner. So if you draw if you plot the points, we are going to get in this decreasing fashion. So you try to approximate to draw up to certain point. You just do the interpolation, you are going to get a sum this point. This is a constant point. So from here draw a straight line. So this is called as the mechanical losses, because you can see clearly mechanical losses means as the speed is almost constant, because the mechanical loss is proportional to the speed. As the speed changes, the mechanical losses changes, but the speed is almost constant for each and everything, so mechanical loss is also constant. So this is called as a mechanical loss, and the remaining part is called as the stator core loss. So remaining part is called the stator core loss or iron loss. So listen carefully. This is called as a mechanical loss, and the remaining thing is called as a stator core loss or iron loss, and the summation is called as the constant losses. So this is operated at a rated frequency. So this is the graph we are going to obtain at a rated frequency. So this is a PC1, PC2, PC3, PC4 and PC5. So we are going to get in this manner. So whenever the supply voltage decreases, the input current decreases, the input power decreases, the constant losses also decreases in this fashion. So if you do the approximate and the interpolation, you are going to get a fixed point, draw a straight line, horizontal line. So this is the mechanical losses, and the remaining part is said to be stator core loss or the iron losses. So we can say clearly that as the speed is nearly equal to constant, the mechanical loss is constant. So with the help of this thing, this is called as a mechanical loss, and this is called as a stator core loss or iron loss of stator. So this is the point that you always have to remember. As the speed is constant, so mechanical loss is a constant. As V is a variable, then iron loss will be variable. So therefore, as the speed is a constant, the mechanical loss is constant. But as the voltage is a variable, so then iron loss will be a variable. So we can say, we can easily get the mechanical losses with this interpolation. So as the speed is almost constant, so mechanical loss is a constant. As the voltage is a variable, then iron loss is also variable. So this is a point that you always have to remember. So mechanical loss is nothing but friction and windage losses. So mechanical loss is nothing but, it is basically friction and windage losses. And already told you, constant losses is nothing but summation of the iron loss and the mechanical losses. So constant losses means it's the summation of the iron loss in a stator. It is basically iron loss in stator plus mechanical losses. It is iron loss in stator plus mechanical losses. So we can say clearly, this is nothing but iron loss in stator plus mechanical losses. And mechanical losses basically means friction and windage losses. As the speed is constant, mechanical loss is also constant. As the voltage is variable, then iron loss in a stator is also variable. So now we are going to discuss the reduced voltage starting methods of high rating induction motors. Reduced voltage starting methods of high rating induction motors. So basically we are going to reduce the voltage for the high rating induction motors. So we are going to reduce the input voltage with the induction motor for the high rating induction motors with the help of some methods. So basically we are going to reduce the input voltage by different methods for the high rating induction motors. The first one is called as stator resistance or reactor start. So stator resistance or reactor start. We will see what is this. So this is the induction motor. So induction motor, this is the induction motor. So therefore, here initially we are going to keep some type of resistors. So by this we are going to reduce the voltage which is incoming to this stator. So stator resistance or reactor start. So we are going to keep the resistance to the input. So we are going to decrease the voltage. So initially V means now it is X into V. The flux is reduced by X into phi. The induced voltage is also reduced by X into V2, and the current is also reduced by X into I2. So as the voltage is reduced, the flux is reduced, the EMF induced in the rotor is also decreased, and the current in the rotor is also decreased. So S is going to lie between 0 to 1. So this is the point that you always have to remember. As the voltage is reduced by X, the flux in the stator is also reduced by X, the EMF induced in the rotor is also reduced by X, and the current in the rotor is also reduced by X. So X is going to lie between 0 to 1. As I have already told you, starting torque. Starting torque is nothing but simply 60 by 2 pi ns into 3 into starting current whole square into R2 by S. I have already told this one. And starting the slip is equal to 1. So therefore this is proportional to starting current whole square. Whereas for the full load torque, it is equal to the 60 by 2 pi capital ns into 3 into magnitude of the starting full load current whole square into R2 by S. So this is also I have already told. So therefore it is proportional to full load current whole square by slip S1, because the remaining factor omega is same for both the things. So it is proportional to this one. So starting torque is proportional to starting current whole square, and the full load torque is proportional to full load current whole square by SF. So now you do the ratio of these two things. The starting torque by full load torque is equal to the starting current by full load current whole square into full load slip. So therefore TST is called the starting torque, and ISC is called the starting current, and IF is called as the full load current, and SF is called as the slip at full load, and DF is called as the torque at full load. So this is the thing that we are going to get. So starting torque by full load torque is equal to ISC, starting current by full load current whole square into full load slip. So now if the starting current is decreased by X, so therefore we can say X into ISC. So if we take the square, we are going to get here, which is X square times the ISC by IF whole square into SF. So the starting current by full load, the starting torque by full load torque is equal to x square into starting current by full load current whole square into slip at full load. So this is a formula that you always have to remember, because we are reducing the starting current also, so therefore x into ISC. This x, if it comes outside, we are going to get x square. So starting torque by full load torque is equal to x square into starting current by full load current whole square into slip at full load. Instead of keeping the resistance, if you keep resistance, power is lost. Instead of that, go for the auto transformer. So this is called as the auto transformer starting. So this is the supply voltage V, and this is the auto transformer. As you are going to vary this one, as you are going to vary these tappings, we can reduce the amount of input voltage to this stator. As the voltage is reduced, the current is reduced, then the flux is reduced, EMF induced in the rotor is decreased, and the current in the current induced in the rotor is also decreased. So therefore we can say, if this is a supply voltage V and this is a line current IL, and the voltage is reduced by X into V and the current is reduced by X into ISC. ISC is called the starting current. The supply voltage is decreased, means the starting current is also reduced. So therefore we can say that the flux is also reduced, which is X into 5, and the EMF induced in the rotor is also decreased by X into E2, and we can say that, and the current which is induced in the rotor is also decreased by X into I2. So write this important point here. In the starter resistance or reactor start also, as the input voltage is reduced, the starting current is also reduced, which is X into ISC. So here I have kept here X into ISC. That is the reason I am going to get X square into ISC by IF whole square into SF. So here also you have to write which is X into ISC, X into starting current. As you are reducing the voltage is reduced, the starting current is reduced, the flux is reduced, EMF induced in the rotor is also decreased, and the current in the rotor is also decreased. So we can say clearly, as the voltage is reduced, the starting current is reduced, the flux in the core is reduced, and the flux in the amount of EMF induced in the rotor is decreased, and the current in the rotor is also reduced. So X is going to lie between 0 to 1. So whereas always input power should be always equal to output power. So listen carefully, always the input power should be always equal to output power. So V1 I1 is equal to V2 I2. For auto transformer, the input voltage is V and the input current is IL is equal to, for the output of the transformer, the input voltage is X into V and the output current is X into ISC. So therefore, if you solve this one, VV cancels. So input current is equal to X square into ISC. So input power is equal to V into IL and output power is equal to X into V into X into starting current. So listen carefully, input power should be always equal to output power. Input power is V into IL and the output power is nothing but XV into XIC. So therefore if you solve this one, we are going to get IL is equal to X square into starting current. So input current is equal to X square into starting current. I have already told one important point, which is starting torque by full load torque is equal to X square into starting current by full load current whole square into slip at full load. So here it is X square. X is called as a basically percentage of tapping. It is basically percentage of tapping. How much percentage you are doing the tapping. X is always lie between 0 to 1. So starting torque is always directly proportional to X square. So you can say clearly the starting torque is always directly proportional to X square, and the starting torque is always greater than the full load torque. So we can say starting torque is always directly proportional to X square and the starting torque is always greater than the full load torque. So now we'll see some more important things regarding this one later. The other type of reducing the voltage is called as a star delta start method. Star delta start method. So you can say clearly star delta start method, how to use this one. Now we will see, always stator is designed in the delta connection. So stator we are going to design in the delta connection, and the rotor we are going to use stator and then delta. So the star connection we are going to use for the starting, and then we are going to go for the delta at the running condition. So listen, the stator is designed is always in the delta connection. So stator is always designed in the delta connection, whereas this rotor is designed as basically star for the starting condition and delta for the running condition with the help of these switches. So with the help of these switches, we can convert at the starting. We can do the connection of the rotor in the star mode, and with the running we can convert this into delta mode. So this is called as the star delta start method. Always the stator is always designed in the delta fashion. Only the rotor winding, during the starting we can do it in the star connection, and during the running we can convert back it to the delta connection. So this is the lines A, B and C. So this is the star connection and also the delta connection with the help of these switches. So star connection at the starting and delta connection at the running. So stator is always designed in the delta. If this is the supply voltage V1, supply current is I1. If the supply voltage is V2, then the input current is I2. So therefore, these coil terminals are A1, A2, B1, B2, C1, C2. If you connect this one to A1, B1 and C1, we are going to get basically, this is called as the delta at running, and this is star at the we can say star at the starting condition. So now the formula will be starting torque by full load torque is equal to 1 by 3 into starting current by full load current whole square into slip at full load, and always V1 by V2 is equal to I1 by I2. So this is the formula that you always have to remember. V1 by V2 is equal to always I1 by I2. If V1 is the supply voltage, the input current is I1. If V2 is the supply voltage, the input current is I2. So V1 by V2 is equal to I1 by I2. So therefore, starting torque by full load torque is equal to 1 by 3 into starting current by full load current whole square into slip at full load. So this is the point that you always have to remember. So this is A1, B1, C1, and this is C2, A2 and B2. The another method is called as the rotor resistance starting. So rotor resistance starting means rotor resistance starting. So this is basically stator we are going to connect in the stator we are going to connect in terms of the star connection, and we are going to give the supply voltages, and the rotor we are going to connect in the star connection, and then we are going to connect to the slip rings. Here we are going to use the shaft. Here also we are going to use the brushes. Through brushes we are going to connect to the external resistance. So rotor resistance starting. So basically we are going to connect the external resistance to the rotor to improve the starting torque of the induction motor. So this is called as the rotor resistance starting, because for the rotor winding we are going to connect the external resistance through brushes, through slip rings to these rotor windings. Then we can improve the rotor resistance starting torque. So these are the different methods that are very useful in the reducing the voltage, because reducing the voltage for starting methods of high rating induction motors. So we can say the first method is called as the stator resistance or the reactor start. Second one is the auto transformer starting method, and the third one is the star delta start method, and the last one is the rotor resistance starting. So these are the different methods we can use for the reducing the voltage at the input of the stator of the high rating induction motors. So now we will discuss one important concept which is called as the voltage control on induction motor. So voltage control on induction motor is a very important concept that we are going to study now in a very detailed manner. So voltage control on induction motor. See, starting torque is always directly proportional to square of the voltage. I have already told you. So because T is equal to 3 into 60 by 2 pi capital Ns into I2 S into E2 square R2 by R2 square plus SX2 whole square. So we can say as the supply voltage increases, the EMF induced in the rotor is also increase. So it is directly proportional to square of the voltage. So starting torque is directly proportional to square of the supply voltage. Full load torque is also directly proportional to square of the supply voltage. And the maximum torque is also directly proportional to square of the supply voltage. So now I am going to draw the graph between the torque and the slip. Let me assume the slip here is 0 and here it is 1. So S is equal to 0 means simply we can say NR is equal to NS, means we can say no load condition. At no load condition we can say it is going to run at the rotor speed is nearly equal to synchronous speed. So therefore slip is equal to 0, means we can say it is a no load condition. Whereas S is equal to 1 means starting condition, because at that condition the speed is equal to, the rotor speed is equal to 0, so S is equal to 1. See, S is going to increase from 0 to 1 in this fashion. So up to 0 to Sm, up 0 to Sm, as S is increasing from 0 to Sm, it's a straight line. So as S increases, the torque is also increases. Whereas from Sm to S is equal to 1, then the torque will decrease. So therefore, as S is increasing from 0 to Sm, then the torque is increases. From Sm to S is equal to 1, the torque will decrease. So this is the graph that you are going to get in this fashion. So now we can say what is the stable region and the unstable region. So this is called as a stable region and this is called as the unstable region. So whenever the slip is nearly equal to 0, so we can say that slip is nearly equal to 0 means something that is nearly equal to 0 in this region. So because it is nearly rotating at NR, so therefore the NR is nearly rotating at NS. So we can say that region is said to be a stable region. So this is called as a stable region, whereas here it is said to be unstable region. See why it is called a stable region, I will explain here. Suppose you take some point here. Suppose I have added the load here. Suppose there is a point here. Suppose I have added the extra load. Suppose it is rotating at some speed, I have added the load. As the load is increased, speed will decrease. Speed will decrease means we can say as the speed will decrease means we can say that the slip will increase. So slip will increase means this point will go to here. So here, so the torque is very high now. So then we can get back to the original position. So listen carefully. In this region, stable region, why it is called a stable region means suppose we take some point here, and now due to some external sudden load, I have added the load. Then what is going to happen basically if I add the load, speed will decrease, so slip will increase. Means the new point will be here. So at the new point, the slip is very high, so the torque is also very high because we need huge torque to drive that more load. So therefore to get back to the original speed. So we can say this is said to be a stable region. Whereas we come to this unstable region, I will explain why it is called the unstable region. Suppose I am operating at this certain speed here. Suppose I added the external load. If I add the external load, the speed will decrease. The speed will decrease means the slip will increase. The slip will increase means this point. So the point will move further down, but the torque is still less. So therefore you can't get back to the original speed. That is the reason it is called as the unstable region, whereas here it is a stable region. So listen carefully, why it is called unstable and unstable means if take any point here, you add the external load suddenly. If you add the external load suddenly, what is going to happen? The speed decreases, so slip increases means the point will go further. So torque is increased to get back to the original speed. Whereas here, if you take any point here, and if you add the external load here, what is going to happen? The speed will decrease, so slip will increase, and the torque is again decreased. So therefore, the torque is decreased, it can't drive that load to make the speed constant, to increase that speed. So definitely we can say that this is said to be unstable region, and this is said to be a stable region. So this is the point that you always have to remember. So whenever you increase the supply voltage, so if you increase the supply voltage, the starting torque, this is called the starting torque will increase, and also the maximum torque will increase, and the full load torque is also increase. Full load torque means at this is the region. So full load means here it will be somewhere here. So we can say as the starting torque increases, maximum torque increases, and the full load torque is also increase. So slip at maximum torque. So slip at maximum torque is equal to R2 by X2, where R2 is the rotor resistance at standstill, and X2 is called as the rotor reactance at standstill. So from this diagram we can say V1 is always greater than, V2 is always greater than, V3 is always greater than V4. So this is the point that you always have to remember for your lifetime. So whenever the supply voltage increases, the starting torque increases, the full load torque increases, and the maximum torque increases. So let me take some torque demand. So this is let me take one straight line passing like this. This is called the torque demand by load. See, as the voltage decreases, as you can see clearly, as the voltage decreases, the slip will increase. So you can see the point is moving like this. So therefore, slip will increase. Demand torque is equal to constant demand. So as the voltage decreases, the slip will increase, because to make the torque as demand as constant, to make torque is equal to constant demand. Then what is going to happen? I have already told you torque is directly proportional to SC2 square means directly proportional to SC to V square. But torque is equal to constant. As the voltage decreases, S must increase. Yes, to make torque is equal to demand constant, as the voltage decreases, slip is increasing. So as voltage decreases, S is increasing. So as S increases, the speed will increase, the rotor speed will decrease. As the rotor speed decreases, I have already told you the rotor copper loss is nothing but slip into rotor input. As the slip increases, the rotor copper loss increases, so efficiency will decrease. So operating point goes out of the stable region. So we can say clearly this point move further, and it can move to the unstable region. So operating point may goes out of the stable region, so speed of motor decreases. So speed of rotor will decrease. So we can say clearly, as the voltage decreases, the slip increases, to make torque is equal to constant demand. So torque is directly proportional to S into V square. For torque is equal to constant, as the voltage decreases, S must increase to make the torque is equal to constant. As the slip increases, the rotor speed decreases, and you can say that rotor copper loss is equal to S into rotor input. As S increases, rotor copper loss increases, so efficiency decreases. So operating point goes out of the stable region, so speed of rotor will decrease. So we can say clearly it goes out of the stable region and it may go into unstable region. So speed of rotor will decrease. So now we will discuss one more important concept, which is called as a frequency control in induction motor. So what is the frequency control in induction motor? That we are going to study in a very detailed manner. Frequency control in induction motor. So I have already told you the general expression of the torque is equal to 3 into 60 by 2 by capital S into S into E2 square R2 by R2 square plus SX2 whole square. At maximum torque, I have already told you, this is a general expression of the torque. At maximum torque, slip is equal to R2 by X2. If you keep the slip in this expression and if you do the simplification, finally we are going to get maximum torque is equal to 3 into 60 by 2 pi ns into E2 square by 2 into X2. So you can see clearly this maximum torque is independent of the rotor resistance. So therefore this is the maximum torque. And the maximum torque is directly proportional to 1 by 2x2. So 1 by 2x2. So 1 by 2h2. This is a point that you always have to remember. Suppose as frequency decreases, the rotor reactance will decrease because x is equal to omega L. As f decreases x2, the reactance of the rotor will decrease. So slip will increase. So we can say clearly as the supply frequency decreases, the rotor reactance decreases. So slip at maximum torque will increase. So therefore similarly, if frequency increases, the rotor reactance will increases. So slip at maximum torque will decrease. So this is a point that you can learn from this one. Suppose for a supply frequency f, the synchronous speed is ns. For a supply frequency f, the synchronous speed is ns. And for the supply frequency f1, what is the synchronous speed? I have already told you ns is directly proportional to f. So therefore, if you do the ratio of these two things, we are going to get ns1 is equal to ns into f1 by f, because ns is directly proportional to f. So therefore, if you do the simplification, we are going to get ns1 is equal to ns into f1 by f. So we are going to get this new synchronous frequency, and we can say new synchronous speed. We are going to basically use the v by f as constant. So voltage by frequency as constant. So v by f is equal to v1 by f1. So we are going to keep this v by f ratio as a constant. But simply we can say v by f ratio as a constant means v by f is equal to v1 by f1. So we are going to use this v by f as a constant. Then we are going to do the further analysis of this one. So if the supply voltage is f, the supply frequency is f, and supply voltage is v, the induced voltage is E2 in the rotor. For the supply frequency of f1 and for the supply voltage of v1, the induced voltage will be, induced voltage is again proportional to there. So you can see that the induced voltage is again proportional to its frequency. So therefore we can say that which is f1 by f into E2. f1 into E2 by f. So f1 into E2 by f. So this is the point that you always have to remember. So for f, for the supply frequency f, the voltage is V and the induced voltage is E2. And for supply frequency f1, the voltage is the supply voltage is V1 and the induced voltage is, which is E21, is equal to E2 into f1 by f. So this is the new induced voltage we are going to get at this condition. For supply frequency f, the rotor reactance is x2. For the new supply frequency f1, the rotor reactance, because that is proportional, so x21 is equal to x2 into f1 by f. So we can say that if you change the f, the ns is changed, the x2 is changed, and the E2 is also changed. So now we will see what is going to happen. So for supply frequency f and supply voltage V and the induced voltage is E2, the synchronous speed is ns and the maximum torque is Tmax. And for the new supply frequency f1 and the new supply voltage v1, but the ratio is same, v by f is equal to v1 by f1, and the induced voltage in the rotor is E21, which is equal to E2 into f1 by f, and similarly ns1 is nothing but ns into f1 by f. This is the new synchronous speed and this is the new maximum torque, just Tmax1. So we are going to see what is the maximum torque we are going to get. Whether you are going to get the same as the previous one or different, we are going to see. So for this new value of the supply voltage and supply frequency with the V by F ratio as a constant, we will see what is the maximum torque. So Tmax1 and mu1 is equal to 3 into 60 by 2 pi ns1 into E21 whole square by 2x to 1, because these are the new values. So 3 into 60 by 2 pi, where ns1 is nothing but f1 by f into ns, and E21 is nothing but f1 by f into E2, and ns is nothing but f1 by f into x2. So you can see clearly this f1 by f is ratios are going to get cancelled. So finally we are going to get the old value, which is 3 into 60 into E2 square by 2 pi ns into 2x2. So 3 into 60 by 2 pi ns into E2 square by 2x2 we are going to get, which is the old value, which is Tmax. So therefore the new maximum torque will be equal to old maximum torque whenever the V by F ratio is constant. So finally I can say the Tmax is also called as the maximum torque or breakdown torque or the pull down torque. So for whenever the V by F ratio is a constant, the maximum torque will be always constant. So maximum torque will be always constant. See, the synchronous speed is always directly proportional to frequency, and the induced voltage in the rotor is also directly proportional to frequency, and the rotor reactance is also directly proportional to the frequency. So these are the points that you always have to remember. So whenever we keep the V by F ratio as a constant, we can say clearly the maximum torque is always same for both the cases, and the synchronous speed will vary, and the EMF induced in the rotor will vary, and also the rotor reactance will vary, but the maximum torque will always be constant. So maximum torque is also called as the Tmax is also called as the maximum torque or breakdown torque or the pull down torque. These are the different names for this Tmax. See, let me repeat this concept again. The frequency control is also called as a V by F control in the induction motor. So the torque original general formula is 3 into 60 by 2 pi capital S into S into E square R2 by R2 square plus S6 whole square. So if you want to know what is the maximum torque, you have to keep the slip at maximum torque, which is R2 by H2. If you keep this one and if you simplification, we are going to get that maximum torque is equal to 3 into 60 by 2 pi ns into E2 square by 2h2. So you can see the maximum torque is directly proportional to 1 by 2h2. See, as the frequency decreases, the rotor reactance decreases, the slip at maximum torque will increase. As the frequency increases, the rotor reactance increases, and the slip at maximum torque will decrease. See, ns is equal to 120 f by p, so ns is always directly proportional to f. So for a given f, the synchronous speed is ns. For the new frequency of f1, the synchronous speed is nothing but just to the cross multiplication, new synchronous speed is equal to ns1 is equal to ns into f1 by f. So V by F ratio we are going to keep it as constant, which is V by F is equal to V1 by F1. So for a given supply voltage F, for a given supply frequency F and a given supply voltage V, and the EMF induced in the rotor is E2. For a new supply frequency F1 and the new voltage supply voltage V1, the EMF induced is nothing but E21 is equal to here F1 E2 into F1 by F. So this is the new induced voltage in the rotor. So we can say clearly therefore for a frequency F, the rotor reactance is X2. For a frequency F1, the rotor reactance, because rotor reactance is proportional to frequency, so X21 is equal to X2 into F1 by F. So we can say clearly for a frequency F, the supply voltage V, the EMF induced in the rotor is E2, and the synchronous speed is ns, and the maximum torque in the rotor is Tmax. For supply frequency of F1, the supply voltage of V1, the EMF induced in the rotor is E21, and the synchronous speed is ns1, and the maximum torque is Tmax1. So now we will see whether these are same or not. Tmax1 is equal to 3 into 60 by 2 pi new synchronous speed, which is ns1 into E21 whole square by 2x21. These are the new induced voltage and the new rotor reactance. So we know these values, just substitute and if you simplify, we are going to get the new maximum torque is always equal to old maximum torque. Now Tmax is also called the maximum torque or breakdown torque or the pull down torque. So always we can say whenever you give the V by F ratio as a constant, always the maximum torque is always constant. So this is the point that you always have to remember. So if you draw the diagram with torque with respect to slip, I have already told you this is S is equal to 0 and S is equal to 1, and this is the maximum slip. I have already told you whenever the slip is 0 to maximum slip at maximum torque, as S increases, the torque increases. From SM to 1, the torque will decrease as S increases. It is inversely proportional to S in here and directly proportional to S here. So this is called as a stable region where this is said to be unstable region. S is equal to 0 means NR is nearly equal to NS, whereas here S is equal to 1 means NR is nearly equal to 0. So therefore we can say this is said to be starting. Here we can say it is said to be, and we can say no load condition. This is a no load condition and it is a starting condition. So at full load, we can say NR is nearly equal to NS means slip is nearly equal to S means this is the operation. So it is said to be stable. It is said to be unstable. I have already told you stable and unstable region explanation also. Suppose if the frequency is increased. So suppose here F is greater than F1. Suppose here F is greater than F1. Then what is going to happen? As F is greater than F1, what is going to happen? As F increases, X2 increases. So slip at maximum torque will decrease. So therefore its value will decrease. Slip at maximum torque will decrease. So therefore SM is always lesser than SM1. So therefore as the frequency increases, so this is F1 and this is F. As the frequency increases, the rotor reactance increases and the slip at maximum torque will reduce. So therefore this value will reduce. So this is the SM is nearly equal to 0. So it will reduce. So therefore, but the maximum torque is always constant. And see, so you can see clearly this is the for this frequency and for this is the frequency. So this is the original frequency. The frequency is now increased. So the graph is going to look in this fashion. So therefore we can say clearly that the starting torque is now reduced. As the frequency increases, we can say that the maximum torque is a constant and the slip at maximum torque will reduce and the starting torque is also reduced. So this is a point that you always have to remember. So one important point that you always have to remember, which is whenever the V by F ratio is a constant, the maximum torque is always constant. As the frequency increases, the slip at maximum torque will reduce and also the starting torque will also reduce. So pure frequency control induction motor. So now we are not going to make any V by F ratio as a constant. Just it is a purely frequency control induction motor. So basically it's a pure frequency control induction motor. So we are not going to take V by F ratio as a constant. It's a pure frequency control. So Tmax formula, what I have already told you, 3 into 60 by 2 pi ns into V2 square by 2 into x2. In ns there is a one frequency f. In x2 also there is a one frequency f. So f into f is called as f square. So 1 by f square. So therefore Tmax is inversely proportional to 1 by f square. Whereas the starting torque, so starting torque is nothing but just to keep at the starting NR is equal to 0, so S is equal to 1. So if we substitute in the general expression, we are going to get 3 into 60 by 2 pi ns into V2 square R2 by R2 square plus x2 square. So you can see clearly x2 square is nothing but x2 is proportional to f, so f square. But in ns also there is a one frequency, so f into f square is proportional to f cube, so 1 by f cube. So Tmax is inversely proportional to square of frequency and the T starting torque is inversely proportional to 1 by f cube. So Tmax is directly proportional to 1 by f square and the T starting is directly proportional to 1 by f cube. Suppose f3 is greater than f2 is greater than f1. So if the frequency increases, what is going to happen? If the frequency increases, the synchronous speed will increase. So synchronous speed will increase. So this is the new synchronous speed N3, NS2 and NS1. So synchronous speed will increase more and more. So now, if this is the new synchronous speed NS3, NS2 and NS1, this is torque with respect to speed, we are going to draw this diagram. So what is going to happen if this is the new synchronous speed NS3, NS2 and NS1? Then I have already told you, as the frequency increases, the maximum torque increases, the maximum torque decreases and the starting torque is also decreases. So therefore, whenever you increase the frequency, the maximum torque decreases and also the starting torque decreases. The starting torque decreases by a factor of 1 by f cube, whereas the maximum torque reduces by a factor of 1 by f square. So therefore, the change in starting torque is very drastically when compared to change in maximum torque. So this is the F1, this is the F2 and this is the F3. So you can see clearly as the frequencies increases, the synchronous speed increases and the maximum torque decreases and the starting torque is also reduces. So we can say this is called as the no load condition and this is called as the standstill condition. At standstill, the speed is equal to 0, so slip is equal to 1. At a no load condition, you can say speed is nearly equal to, the rotor speed is nearly equal to ns, so slip is equal to 1. So we can say in very simple case. So therefore, whenever the frequency increases, the synchronous speed increases and the maximum torque decreases and the starting torque decreases and the maximum is directly proportional to 1 by f square. and the starting torque is directly proportional to 1 by F cube. So these are the points that you always have to remember. So now we are going to learn another new concept which is called as the starting torque or the fundamental approach. The expression of the starting torque by the fundamental approach now we are going to study in a very detailed manner. So expression of the starting torque through the fundamental approach that we are going to study. So starting torque is directly proportional to E2 into I2 into cos phi 2. These things I have already told you. So starting torque is directly proportional to E2. What is the value of I2? At starting torque, at starting condition, I have already told you that the slip is nothing but at starting condition, the NR is equal to 0, so slip is equal to 1. The EMF induced is E2 and the current is I2 and the power factor and the reactance, the resistor is R2 and the reactance is X2. So therefore, E2 into what is the value of I2? I2 is equal to E2 by under root over R2 square plus X2 square into what is the cos phi 2, which is R2 by under root over R2 square plus X2 square. So if you do a multiplication of these two things, finally we are going to get the starting torque is directly proportional to E2 square into R2 by R2 square plus X2 square. So if you want to remove the proportionality constant, keep a constant which is called as the K. So starting torque is equal to K into E2 square R2 by R2 square plus X2 square. I have already told you K is nothing but 3 into 60 by 2 pi capital NS. All these things we have already studied in our previous classes. So now we can say EMF which is induced in the rotor is directly proportional to flux which is present in the air gap. So therefore, whatever the flux is directly proportional to supply voltage. So whenever the supply voltage increases, the flux in the rotating flux is going to get increased. Whenever the rotating flux increases, then the EMF induced in the rotor is also increases. So this is the point that you always have to remember. As I've already told you, the starting torque is directly proportional to E2 square. So E2 means it is again proportional to supply voltage whole square. So therefore V is called as supply voltage. So therefore we can say starting torque is always directly proportional to supply voltage whole square, because E2 is directly proportional to the rotating flux, it is directly proportional to supply voltage. So therefore starting torque is directly proportional to square of the EMF induced in the rotor, or simply we can say starting torque is directly proportional to square of the supply voltage. So T starting torque is directly proportional to V square. So therefore starting torque is also directly proportional to R2. You can see clearly through the expression, because starting torque is equal to 3 into 60 by 2 pi capital S into E2 square into R2 by R2 square plus X2 square. So starting torque is directly proportional to rotor resistance. So therefore only up to only a suitable value of R2. So up to only suitable value of R2. So therefore whenever the rotor resistance increases, the starting torque increases. So this is the thing that you always have to remember. So whenever the rotor resistance increases, the starting torque increases up to only suitable value of the resistor R2. So now we are going to figure out the condition for the maximum starting torque. So what is the condition for the maximum starting torque? So starting torque is directly proportional to R2 by R2 square plus X2 square. I will assume that remaining everything is constant except R2 is a variable. So only R2 is a variable I am going to assume. Remaining all other parameters are constant. So I want to find at what value of R2 I am going to get the starting torque as maximum, which is D start. So we have to do the differentiation of the above expression with respect to R2 is equal to 0. So d TST by dR2 is equal to 0. So if you solve this one, we are going to get R2 is equal to X2. So therefore R2 is equal to X2. At this condition we are going to get the starting torque as a maximum value. So maximum starting torque, the condition is whenever the R2 is equal to X2, we are going to get the maximum starting torque. So therefore the starting torque maximum value, is directly proportional to 1 by 2x2. So 1 by 2x2, because you can see clearly. So therefore if you substitute R2 is equal to X2 in the starting torque expression, then definitely we can say that we are going to get, which is R2. So if you substitute R2 is equal to X2, so we are going to get here R, which is X2 by 2x2 whole square. So therefore 1 by 2x2 we are going to get. So if you substitute R2 is equal to X2 in this expression, then we are going to get finally like this. So starting torque maximum value is directly proportional to 1 by 2x2. So now we will discuss the running torque fundamental approach. So running torque fundamental approach we are going to see in a very detailed manner. So we can say full load torque, or we can say any torque. So or we can say running torque. So running torque is directly proportional to EMF induced in the rotor into current induced in the rotor into cos of phi 2 dash. So therefore EMF induced in the rotor is nothing but simply we can say that K, which is simply some directly proportional to K2 into E2. Here I2 dash is nothing but which is I have already told you in the running condition. So in the running condition I have already told you in the running condition the current I2 dash is nothing but S into E2 by under root over R2 square plus Sx2 whole square. Whereas cos phi dash is very simple, which is equal to R2 by under root over R2 square plus Sx2 square. So if you solve this one, we are going to get that the full load torque, or we can say torque of the induction motor at the running condition is directly proportional to S into E2 square R2 by R2 square plus Sx2 whole square. So this is the formula that we are going to get. So in general, TF is called as the full load torque or the running torque. So always E2 dash is equal to, see E2 dash is nothing but K1 into phi, which is equal to K2 into E2. So therefore E2 dash is nothing but you can replace E2 dash is equal to some K1 into phi is equal to, we can write K2 into E2, because whenever the flux increases, E2 dash is increases, EMF induced in the rotor, or simply we can also write it is equal to K2 into E2. So that is the reason I have substituted E2 dash is nothing but K2 into E2. So therefore I am going to get in this format, which is the torque at the running condition or full load torque is equal to K into S E2 square R2 by R2 square plus Sx2 whole square. So K is nothing but simply 3 into 60 by 2 pi capital Ns. So therefore this is the expression of the general torque of the induction motor, which is 3 into 60 by 2 pi into capital Ns into S E2 square R2 by R2 square plus Sx2 whole square. So now we will see what is the condition for the maximum running torque. So at what condition we are going to get the maximum running torque. So we can say the expression of the torque, the running torque is directly proportional to S into R2 by R2 square plus Sx2 whole square, because I am going to assume E2 all other parameters are constant. Let me take this as is equal to 1 by y. So what is the y? Y is inverse of this one, R2 square plus S square x2 square by SR2. So if you take the fractions, we are going to get y is equal to R2 by S plus Sx2 square by R2. So therefore I want to do the differentiation of this one with respect to ds is equal to 0. So therefore at what ratio we are going to get this as is equal to 0. So differentiation of dy by ds is equal to 0. We are going to get R2 is equal to S into x2. So S is equal to R2 by x2. So therefore we can say at this slip we are going to get the maximum torque. So therefore at this slip we are going to get the maximum torque. So this is the slip at which we are going to get the maximum torque, which is the is equal to S is equal to R2 by x2. So SM is called as the slip at the maximum torque we are going to get, which is the ratio of the R2 by x2. So if you substitute S is equal to R2 by x2 here and if you do simplification, we are going to get the maximum torque is directly proportional to 1 by 2x2. So therefore the maximum torque we are going to get is directly proportional to 1 by 2x2. So during running condition, we can see clearly what is going to happen during running condition. So during running condition, NR is nearly equal to NS. So as NR is nearly equal to NS, S is very less value. S is very small value. So if S is very small, then S into x2 whole square is neglected, because S square is again very small. So we are going to neglect this term. So in the general expression of the torque, so this term is neglected. Then what is the running torque, which is equal to 3 into 60 by 2 pi capital S into S into E2 square R2 by R2 square plus Sx2 whole square. As Sx2 whole square is neglected, we are going to get this one. So here R2 and R2 are going to get cancelled. Finally we are going to get 3 into 60 by 2 pi capital S into E2 square by R2. So you can see clearly the running torque is directly proportional to E2 square. It is inversely proportional to 1 by R2. It is directly proportional to S by R2. So therefore when supply voltage is constant. So simply we can say at running condition, or we can say in the stable region, torque is directly proportional to SV square by R2. So therefore this is the case always because we always operate the induction motor in the stable region. So torque is directly proportional to SV square by R2. So S into E2 square by R2, because S into X2 whole square, S into X2 square is very, very small, we are neglecting it, then we are going to get like this. So therefore we can say that the torque is directly proportional to S into E2 square by R2, or simply we can say torque is directly proportional to S into V square by R2. So therefore this is the thing that you always have to remember. So whenever the supply voltage is constant, you are going to get these variables. So the running torque is directly proportional to SV square by R2. This is the case that you always have to remember. This is the condition that we are going to use only in the stable region of operation. So now we will understand some torque slip characteristics. The torque slip characteristics that we are going to understand in a very, very detailed manner. So I have already told you the running torque is nothing but, or full load torque or running torque is directly proportional to S into E2 square R2 by R2 square plus SX2 whole square. This is the general expression of the torque. So during low slip region, I have already told you, in the stable region, or we can say in the stable region, NR is nearly equal to NS, so slip is nearly equal to 0. So we are going to neglect this term because S square is still very low, because S itself is very less, S square is again less. So we are going to neglect this term. Then finally we are going to get like this: torque is directly proportional to S E2 square by R2, because R2 are cancels. We are going to get, this is the expression we are going to get during the low slip region. So therefore we can say torque is directly proportional to S into E2 square by R2, or simply S into V square by R2. So you can see clearly torque is directly proportional to slip S when E2 and R2 are constant. So therefore in the low slip region, whenever the S value increases, the torque is also increases. So this is a point that you always have to remember. That is the reason I have already told you, whenever the S is changing from 0 to slip at maximum torque, then we can say torque is also increases. So therefore torque is directly proportional to S during the low slip region. Whenever the S is changing from 0 to slip at maximum torque, the torque is also increasing, that is proportional to slip. So during high slip region, means I have already told you, high slip region is called as the unstable region. So whenever the S is very, very high, it is called as the unstable region. So therefore S into X2 whole square is very, very high when compared to R2. So we are going to neglect the R2. So if you neglect the R2 square, then definitely we can say that. So we can say that simply we are going to get like this: S into E2 square R2 by SX2 whole square. So listen carefully, S into E2 square R2 by SX2 whole square. So SS cancels, we are going to get finally E2 square R2 by S into X2 square. So this is the thing that we are going to get finally. So therefore this is square, basically S into X2 whole square is greater than the R2 square. So therefore R2 square is neglected. This is basically R2 square. So R2 square is neglected. So here we can say it is R2 square. So R2 square is neglected. So therefore we can, if you neglect the R2 square and if you simplify, we are going to get E2 square R2 by S into X2 square. So this is the expression we are going to get in the high slip region. So we can say clearly torque is inversely proportional to S. So that is the reason I have already told you, whenever the S is changing from slip at maximum torque to S is equal to 1, we can say that the torque is going to get decay. Whenever the S increases, the torque will decay. So therefore it is inversely proportional to S. So therefore when we assume that E2, R2 and X2 are constant. So I have already told you, in the stable region torque is directly proportional to S. In the unstable region torque is inversely proportional to S. So therefore in the stable region torque is directly proportional to S, and in the unstable region torque is inversely proportional to S. So this is the point that you always have to remember. We can say in the stable region, or we can say low slip region, we can say that S into X2 whole square is always lesser than the R2, whereas in the high slip region S into X2 whole square is always greater than the R2 square. So this is a thing that you always have to remember. So therefore we are going to get the expressions, the torque expressions in the low slip region or the stable region, and the torque expression in the unstable region, or we can say in the high slip region. All these things I have already told you. So during no load condition, what is going to happen? So during no load condition, suppose if you are not going to keep any load, then definitely the rotor speed is nearly equal to synchronous speed, then slip will be nearly equal to 0 because rotor speed is equal to ns, so slip will be nearly equal to 0. Then what is the value of s into e2? As s itself is nearly equal to 0, so s into e2 is nearly equal to 0. Then what is the value of the current which is induced in the rotor? It is also nearly equal to 0. So what is the torque which is produced in the rotor? See, as s itself is equal to 0, so torque is also nearly equal to 0 because in the stable region, torque is directly proportional to s. As s is equal to 0, torque is nearly equal to 0. So therefore, we can say that only rotational losses will happen. So therefore, only rotational losses will happen. So therefore, we can say that I already told you during no load condition, the output power is equal to 0 because we are not keeping any load. So output power is equal to 0. Whatever the input power should be gone in terms of the losses. So losses I have already told you so many things. So therefore, so only rotational losses are going to get happen. See, only losses are whatever the input power, it is taken by the losses. So now we will understand the torque slip characteristics. So torque slip characteristics of the induction motor that we are going to study in a very detailed manner. So you can see clearly this is the speed and also with respect to slip. So this is the y-axis is the torque. So now this is the s is equal to 0. This is called as the slip at maximum torque and this is the slip is equal to 1. So this is the speed. Here speed is the rotor speed is equal to 0 and here rotor speed is equal to the synchronous speed. So whenever the rotor speed is equal to synchronous speed, whenever the rotor speed is equal to synchronous speed, we can say that whenever the rotor speed is equal to synchronous speed, slip is nearly equal to 0, and whenever the rotor speed is equal to 0, slip is equal to 1. So this is called as the no load condition and this is called as the standstill condition or the starting condition. So this is called as the no load condition and this is the standstill condition or starting condition. So this is called as the slip at maximum torque, which is Sm is equal to R2 by X2. So S is increasing from here to here and speed is increasing from here to here, both are opposite manner. So S is equal to 0 to Sm, it is called as a low slip region. So our low slip zone, it is said to be a stable region. I have already told the meaning of stable region and unstable region. So this is said to be a stable region and this is unstable region. So in a stable region, whenever the S increases, the torque is also increases in the same proportionate. So as S increases, the torque is also increases in the same proportionate. So torque is directly proportional to S here. Whereas from Sm to S is equal to 1, in this region, whenever the slip increases, the torque decreases because both are inversely proportional. It is called as a high slip zone. So this is low slip zone and this is high slip zone. So we are going to get like this. And I already told you the approximate expression of the torque in this stable region, which is equal to S into V square by R2. Whereas in the unstable region, the approximate expression is V square R2 by S x2 square. All these things I have already told you. So now what is going to happen basically, this is the stable region and this is the unstable region, and maximum torque is always, it is directly proportional to 1 by 2x2. You can see clearly it is independent of the rotor resistance. It is only depending on the rotor reactance. So slip at maximum torque is R2 by x2. So this is, see, we can say this is called as the initial torque or the starting torque because it is a standstill condition. So this is the starting torque which is produced by the induction motor and this is the maximum torque which is produced by the induction motor. So whenever the rotor speed is equal to 0, then slip is equal to 1. It is called as the standstill condition or the starting condition. So T final, it is called as the starting torque or the blocked rotor torque. So T final is also called as the starting torque, or we can simply call it as the blocked rotor torque. So whenever the speed is equal to 0, or we can say standstill condition, so slip is equal to 1. So therefore T final is also called as the starting torque or the blocked rotor torque. These are the different names for this T finally. So therefore starting torque or the blocked rotor torque. So these are the some of the different names of starting torque. Starting torque is also called as the blocked rotor torque. So finally we are going to study the torque slip characteristics of each and everything in a very detailed manner. So you can see clearly this is the torque and this is the slip. I already told you this is the S is equal to 0 and this is the S is equal to 1. So therefore this is Sm, slip at maximum torque is equal to R2 by x2. So this is called as the low slip region. So in the low slip region, I have already told you whenever the S increases, the torque increases. So therefore torque is directly proportional to S. Whereas from Sm to S is equal to 1. So this is called as a high slip region or unstable region. Torque is inversely proportional to S. As S increases, the torque will decrease. So whenever S is equal to 1 means the rotor speed is equal to 0. This is called as the starting condition or the standstill condition. So therefore the torque which is called as the starting torque, it is TST or T starting torque. Whereas here S is equal to 0 means we can say NR is nearly equal to NS. So therefore we can say it is a no load condition. Whereas this is called as the stable region and this is called as the unstable region. I have explained why it is called the stable and why it is called as the unstable. And this is the maximum torque which is produced by the induction motor, and it is directly proportional to 1 by 2x2. It is independent of the rotor resistance. So this is the maximum torque which can be produced by this motor. So now this is called as the full load torque. So this is called as a full load torque, and the corresponding it is called as a full load slip. So always we try to operate. This is called as the operating zone, safe operating zone. So this is called as a safe operating zone. S is equal to 0 to this point, which is somewhat 0.1 like that. So S is equal to 0 to S is equal to 0.1. It is called as the safe operating zone. So this is the point that you always have to remember. Suppose there is a demand torque. Suppose there is a demand torque. So this is the demand which is produced by some load. So this is the demand means the torque should, the rotor should produce, the induction motor should produce a torque of this manner. So this is called as the full load slip and full load torque. And always maximum torque is somewhat nearly 2.5 to 3 times the full load torque. So listen carefully. The maximum torque is sometimes is nearly equal to 2.5 to 3 times the full load torque, and the starting torque is nearly equal to 1.5 times the full load torque. So you can see clearly starting torque is greater than full load torque, and also the maximum torque is also greater than the full load torque. So this is a point that you always have to remember. Starting torque is always greater than the full load torque, and the maximum torque is also greater than the full load torque. So we can say maximum torque is greater than starting torque, and the starting torque is greater than the full load torque. So maximum torque is nearly 2.5 to 3 times the full load torque, and the starting torque is nearly equal to 1.5 times the full load torque. So this is the maximum load that you can see. This is the maximum load that you can apply, not more than this. If you apply more than this, if you apply a load which has a torque demand more than this, then this motor will never drive that one, because its maximum torque is always lesser than the demand, so it will never drive this one. But if any torque demand is lesser than this one, lesser than the starting torque, yes, it can drive it. Yes, it can drive it. So this full load is called as this full load is also called as the rated load or the full load. So this full load is also called as the rated load or the full load. The corresponding is called as the SF, and the corresponding torque is called as the TF. Because there is a load has a certain demand, torque demand, and for the corresponding slip is called as the, let me assume it is S1. So TF is called as the full load torque or the rated torque, and the maximum torque is directly proportional to 1 by 2x2. And I have already told you operating zone, safe operating zone is 0.02 to 0.08 is a safe operating zone. So EMF which is induced in the rotor at full load lies between the EMF induced in the rotor at slip 0.02 to slip 0.08. So EMF which is induced in the rotor at the full load lies between the EMF induced in the rotor with a slip of 0.02 to with a slip of 0.08. See, for S greater than 1, this is called as a plugging or braking zone. So for S greater than 1, it is called as a plugging or braking zone, because S is greater than 1 only when the rotor speed and the synchronous speed are opposite of each other. So whenever the rotor speed and the synchronous speed are opposite of each other, then only we can say it is called as a braking or we can say braking zone or plugging zone. So we try to off the rotor speed. So by producing the synchronous speed which is opposite to the rotor, then we can say that it is said to be, then the slip is greater than 1. It is called as a plugging or the braking zone. So plugging means we are reversing the supply, so synchronous speed will reverse. So therefore, because of that, the rotor speed will decrease. So slip is now greater than 1. So it is called as the plugging mode or the braking zone. Suppose, let me analyze some special case here. Suppose there is a load which has a torque demand constant. So torque demand constant, I have already told you we always operate in a stable region. In a stable region, torque is directly proportional to S V square by R2. Let me assume the rotor resistance is same. So therefore torque is directly proportional to S V square. So therefore we can say that simply V minimum square into Sm is equal to V1 square into S1. So therefore V minimum whole square into Sm is equal to S1 square into S1, because whenever the slip is maximum, so this is the maximum slip which can get in a stable region. So this is the maximum slip. This is the slip at maximum torque we can get. So if S is equal to 0 and this is the Sm, so this is higher when compared to here. So this is the maximum. So therefore slip is maximum, is voltage should be minimum. Then only torque is constant. So this is V1 square into S1. So if you do this one, V minimum by V1 is equal to under root over S1 by Sm. So therefore Sm is called as the slip at maximum torque and S1 is the slip at a particular load demand. So S1 is the slip at the particular load demand. So we can say clearly torque demand is equal to constant is equal to SV square. So if we need maximum slip in a stable region, then definitely voltage should be minimum. So maximum and minimum is nothing but constant. So this is V1 square into S1. So S1 is the slip at the corresponding load demand. So therefore if you do the ratio, V minimum by V1 is equal to under root over S1 by Sm. So this is a very important relation that you are going to get. So for this load demand, if you draw a straight line in the stable region, we are going to get a certain point which is called as the S1 slip. Corresponding to this speed, we are going to get a slip which is called as the S1. In the stable region, the maximum slip we are going to get which is R2 by X2 at the maximum torque. So this is the point that you always have to remember. I have already told you why it is called a stable region and why it is called as a unstable region. And let me repeat it again here. Suppose if you take any point in the stable region and suddenly the load is increased. Whenever the load increases, the speed decreases. So therefore, whenever the speed decreases, we can say slip increases, means the point goes here. So now torque is increased. Torque is increased by the induction motor to make the speed increases. So therefore it will come back to the original position. Suppose if the load is decreased, what is going to happen? Suddenly if the load is decreased, then definitely speed will increase. So therefore speed increases means slip decreases. So now slip decreases. So therefore what is going to happen? Now torque reduced. So when the torque reduced, again the speed will come back to its original position. So therefore we can say speed will now decrease, so slip will increase, so it will come back to the original position. So this is called as a stable region, but here it is reverse. Suppose if you take any point here, suppose suddenly a load is increased, then what is going to happen? If load is increased, the speed will decrease, so slip will increase. So slip increases means the point will go further. Again torque is reduced. So again torque is reduced means again speed will decrease. So same thing, you are going to get a unstable region. Suppose if the load is decreased, what is going to happen? If the load is decreased, the speed will increase. So speed will increase, so slip will decrease. Slip will decrease means you are going to get here. So again the torque is increased, again the speed will increase, again the speed will increase means again the slip will decrease. So you are going to get like this. So you are never going to get a stable region here. So always you are going to get a stable region. If due to some disturbance, if the speed is increased or decreased, suppose due to some disturbance, if the speed is increased, then this motor is try to reduce that speed and make it to the stable region. That is called as a stable region. Suppose due to some sudden disturbance, if the speed is increased, then this motor is going to decrease its torque. So therefore the speed will come back to its original position. That is the meaning of the stable region. So now we are going to discuss about the changing R2 by using slip ring induction motor. So when we are going to increase the rotor resistance with the help of this slip ring induction motor. This is not possible in the squirrel cage induction motor, but this is possible only in the slip ring induction motor. So by using the slip rings, we are going to add the external resistance to the induction rotor, which is called as the slip ring induction rotor. And now you will see what is the change of the graph of the torque with respect to slip. As I have already told you, this is the torque and this is the slip. So whenever the slip is equal to 0, it means that the rotor speed is equal to synchronous speed under the no load condition. Whereas whenever the slip is equal to 1, we say that here the rotor speed is equal to 0, we can say it is said to be starting condition or standstill condition. So now the Sm is the slip at which we are going to get the maximum torque in the induction motor. As I already told you, whenever the slip is increasing from 0 to Sm, the torque is directly proportional to S. So whenever the S increases, the torque is also increases. Whereas from Sm to S is equal to 1, as the slip increases, the torque will decrease. So I have already told this one. So let me assume this is the first graph we are going to get. This is called as the R2 resistance and the starting torque is TS1. So what happens if I increase the resistance? If I increase the resistance, which is R2 dash, whenever I increase R2 dash, so we can say that the Sm, the slip at maximum torque, Sm is equal to R2 by X2. As R2 increases, the slip at maximum torque is also increases. So this will move to the left side. So therefore, as this moves to the left side, so we can say the maximum torque is independent of the rotor resistance. It will remain the same. So this graph will shift here. So therefore, the new one will be maximum here and it goes to this direction. Similarly, again you increase the R2. Again you will go like this. Again you increase it. Again you are going to get like this. So we can say that at R, so this is the starting torque 1, starting torque 2, starting torque 3. So TS1, TST1 is the starting torque at the resistor R2 and TS2 is the starting torque resistor at R2 dash, and this is the TST3 is the starting torque at the rotor resistance R2 double dash. And now we can say the starting torque itself is equal to maximum torque at the R2 triple dash. So we can say clearly that this is the maximum starting torque that we can produce. Again, if you go for the R2 4 dashes, it is greater than this one, so you can say clearly this is the maximum torque you are going to get in this coordinate, but the starting torque is going to get decay. So after R2 triple dash, the maximum torque is still the same, but the starting torque is going to get decrease. But from here to here, the starting torque increases, but after that the starting torque will decrease. So we can say clearly that R2 4 dash is greater than R2 triple dash is greater than R2 double dash is greater than R2 dash is greater than R2. Therefore, T max is greater than TST is greater than TS2 is greater than TS1. So what I am trying to say is, if you increase the resistance up to certain limit, the starting torque will increase. So listen carefully. If you increase the rotor resistance, it will increase up to a certain limit. After that, even if you increase the rotor resistance, the starting torque will decrease. This is the beautiful meaning of this one. So listen carefully. If you increase the rotor resistance, the starting torque will increase only up to a certain limit. After that, it will decrease. So up to a certain value of rotor resistance, if you increase the rotor resistance, the starting torque will increase. But after that, the starting torque will decrease even if you further increase the rotor resistance. This is the beautiful of this concept. So now I want to, this is called as the at S is equal to 1, the starting torque itself is equal to maximum torque. So I've already told you slip at maximum torque Sm is equal to R2 by X2, but at this case we are going to apply this concept. So at this case, now I am going to apply the concept, which is S is equal to slip at maximum torque is equal to, at that condition the rotor resistance is R2 triple dash by X2. As I have already said, here at the starting here slip is equal to 1, so therefore we can say then R2 triple dash is equal to X2. So what happens, there is another new case, what happens if R2 is equal to X2? The full region is a stable zone. So whenever the R2 is equal to X2, the full region is said to be stable zone, because we can see clearly R2 is equal to X2 means we are going to get the maximum torque. See, we are going to get the maximum torque at a slip which is Sm is equal to R2 by X2 which is equal to 1. So at S is equal to 1, we are going to get the starting torque itself is equal to maximum torque. So you are going to get a straight line. So this is said to be full stable zone. So this is called as a full stable zone. So you are going to get the full stable zone. So we are going to get the full stable zone here. So from S is equal to 0 to S is equal to 1, we are going to get the full stable zone. This is what we are going to get. See, whenever you increase the rotor resistance, this is the graph that you are going to get. This is for R2, this is for R2 dash, this is for R2 double dash, this is for R2 triple dash, and this is for R2 4 dashes. So here, as you increase the rotor resistance, you can see clearly the stable region is increasing. The stable region is increasing, and finally up to here, this is the for R2 triple dash. This is the full stable region. So from S is equal to 0 to S is equal to 1, this full is said to be a stable region. This is the simple concept. So now for any constant load demand, for any constant load demand. Now we will analyze the above graph. So same thing, torque with respect to slip. See, this is for R2, this is for R2 dash, and this is for R2 double dash. I have already told these graphs. Let me assume a load has a torque demand, so constant torque demand. Then you can see clearly R2 double dash is greater than R2 dash is greater than R2. All these things I have already told you. So as resistance increases, the slip increases. As you can see clearly, for a constant torque demand, so this is operating point for the R2, this is the operating point for the R2 dash, and this is the operating point for the R2 double dash. But as the rotor resistance increases, the slip increases. Slip increases means the rotor speed decreases. So therefore the rotor copper loss is equal to slip into rotor input. So as slip increases, the losses in rotor, the copper losses in rotor increases for constant load demand. So efficiency decreases. So as the rotor resistance increases, the slip increases. So therefore the operating point goes from here to here. So therefore the slip increases, rotor speed decreases. As the slip increases, the rotor copper loss increases. So for the constant load demand. This is a very important concept that you always have to remember for your lifetime. If R2 is greater than X2, then maximum torque occurs in the braking zone. So I have already told this one, when R2 is greater than X2. So when R2 is greater than X2 means we can say the slip at maximum torque will start. Whenever the R2 is greater than X2, we can say that slip at maximum torque is R2 by X2, which is greater than 1. So therefore we can say that the maximum torque will occur in the braking zone, because from S is equal to 0 to S is equal to 1, it is said to be a braking mode. It is a motoring mode. For S greater than 1, it is said to be a plugging or braking zone. So therefore, whenever the R2 is greater than X2, the slip at maximum torque is greater than 1. So therefore, the maximum torque is going to occur in the braking zone or the plugging zone. So therefore, the starting torque will decrease. So therefore, we can say that if R2 is greater than X2, then the maximum torque is going to occur in the plugging zone or the braking zone. So in the braking zone, I have already told you, in the braking zone, see, we are going to stop the motor by reversing the polarity of the supply. So whenever you reverse the polarity of the supply, the relative magnetic field is also going to get reversed. So NR and NS are going to move in the opposite direction. So the relative speed is nothing but NS plus NR, because they both are moving in the opposite direction. The relative speed is Ns plus Nr. If they move in the same direction, the relative speed is Ns minus Nr. But now they are moving in the opposite direction, which is Ns plus Nr by Ns. You can say clearly this is greater than 1. So we can say whenever the R2 is greater than X2, the maximum torque is going to occur in the plugging mode or the braking zone. Then slip is equal to Ns plus Nr by Ns. So now we are going to analyze one important visual concept, which is called as the rotor resistance control. Rotor resistance control. So rotor resistance control means same thing. We are going to increase the resistance of the rotor. I have already told you the slip at maximum torque is equal to Sm is equal to R2 by X2. So this is the slip at which we are going to get the maximum torque. And here I have already told one important point in the stable region. In the stable region, the slip is very low. So therefore S into X2 whole square is very less than the R2 square. So we have to neglect the S into X2 whole square. Finally, you are going to get, which is torque is directly proportional to S into E2 square by R2. So this is what we are going to get. Let me assume supply voltage is a constant. So we are going to take it as a V as a constant. Then we are going to get torque directly proportional to S by R2. This is in the stable region of operation. So now you can see clearly in this graph. So therefore, this is the slip is equal to 0 and slip is equal to 1. Slip is equal to 0 means Nr is equal to Ns. It is said to be no load condition. So whereas S is equal to 1 means Nr is equal to 0, it is said to be Nr is equal to 0 means standstill condition or the starting condition. So therefore, we can say that here for R2, so this is the graph that we are going to get. So this is the graph that we are going to get here as the rotor resistance increases. So as the rotor resistance increases, the slip at maximum torque increases. So slip at maximum torque increases. So this will move to here, but the maximum torque is independent of the rotor resistance. So maximum torque will remain the same as the previous one. So whenever the rotor resistance, see I have already told you, for S is equal to 0 to S is for Sm, the it is a low slip region or it is a stable region, so torque is directly proportional to S. As S increases, the torque is also increases in a straight manner. Whereas from Sm to S is equal to 1, it is said to be a high slip region, or you can say unstable region. So therefore, as the slip increases, the torque will decrease. And we already told this point. Here, this is the graph for R2, and this is the graph for R2 dash. So whenever the R2 increases, the maximum torque is remains same, and the slip at maximum torque increases, and the starting torque is also increases. So these are the points that you always have to remember. So starting torque will increase only up to a certain limit of increase of rotor resistance. After that, the rotor resistance will, the starting torque will decrease, even if you increase more than that. So listen carefully. If you increase the rotor resistance, the starting torque will increase only up to a certain limit. After that, it will decrease because the maximum torque is going to occur in the braking zone or plugging zone. So therefore, now here R2 dash is greater than R2. So for R2 dash is greater than R2, let me assume there is a constant torque demand. So there is a constant torque demand. So for this R2, this is the operating point. For R2 dash, this is the operating point. So first operating point slip is S1, second operating point slip is S2. So whenever the R2 increases, so whenever the R2, the rotor resistance increases, for constant torque demand, the slip increases for the constant torque demand. So whenever the slip increases, I have already told you, rotor copper loss increases, so efficiency will decrease. So this is the point that you always have to remember for your lifetime. So whenever the rotor resistance increases, the slip increases. You can see clearly slip is increases. So for a constant torque demand, so therefore as slip increases, rotor copper loss is equal to slip times the rotor input. As slip increases, the rotor copper loss increases and the efficiency decreases. As the slip increases means the rotor speed decreases. So these are the things that are going to happen for a constant torque demand whenever the rotor resistance is increases. So now the general expression of torque is equal to T is equal to 3 into 60 by 2 pi capital S into S E2 square R2 by R2 square plus S X2 whole square. So this is called general expression of torque. Where I have already told one important point, for low slip region is also called as a stable region. For stable region, S into X2 whole square is very less when compared to R2 square. So we are going to negate this term. So we are going to get finally S into E2 square by R2. Because R2 cancels, so we are going to get R2. But here Ns, there is a frequency F. So therefore, Ns is equal to 120 F by P. So therefore, we are going to get F here. So therefore, finally, you can say torque is directly proportional to S into V square by R2 into F. This is the torque expression in the stable region, and this is the important relation that you always have to remember. Torque is directly proportional to S into V square by R2 into F. It is a very important formula. It is almost used in every numerical. So torque is directly proportional to S into V square by R2F. This is the formula for the stable region of operation. So slip power frequency in induction motor. So slip power frequency in induction motor. This is a very new concept. Slip power frequency in induction motor. See, injecting voltage into rotor at a slip frequency or rotor frequency. So we are going to inject the voltage into rotor at a frequency of slip frequency or rotor frequency. Either we can go for the addition process or we can go for the operation or subtraction process. So slip power frequency in induction motor means we are injecting the voltage into rotor at a slip frequency or rotor frequency either in addition process or either in the operation or the subtraction process. So slip power frequency in induction motor means we are injecting the voltage into the rotor at a slip frequency or the rotor frequency either in addition process or either in operation or subtraction process. Then we will see what is going to happen with these effects. So slip power frequency in induction motor means we are injecting the voltage into rotor at a slip frequency or rotor frequency either in addition process or in a operation or subtraction process. And now we will see what are the effects of this one. Suppose if you are going to go in the addition process, then what are the effects we are going to see? As I have already told you, in the stable region, torque is directly proportional to S into V square by R2 into F. So let me assume R2 and F are constant. So we are going to get torque is directly proportional to S into V square or S into E2 square. Suppose if the torque is equal to constant. So suppose for torque is equal to constant, what is going to happen? As the torque is equal to constant, see, suppose there is a torque demand of constant torque demand. As I have already told you, by addition, EMF induced in the rotor will increase because we are externally injecting the voltage into rotor at a slip frequency in addition process. So overall induced voltage in the rotor will increase. So as E2 increases, we can say that torque demand should be constant, so therefore slip will decrease. So slip decreases means the rotor speed must increase. So we can say that very important point that you always have to remember. If you injecting the voltage in a rotor at a slip frequency or rotor frequency in an addition process, if you are injecting externally the voltage into rotor, and this voltage is adding the EMF induced, so overall induced voltage in the rotor will increase. So for a constant torque demand, the slip must decrease to make torque is equal to constant. As the slip decreases means the rotor speed will increase. So by injecting the voltage externally into the rotor, if it is an additive property, then definitely the speed will increase for a constant torque demand. Suppose what happens for the opposition, or we can say subtraction case. So if you are injecting the voltage into the rotor but which is subtracting the original EMF induced in the rotor, so overall value will decrease. So therefore torque is directly proportional to S into Vt square. For a constant torque demand, as the EMF induced in the rotor overall value decreases, so therefore the slip should increase to make torque is equal to constant. As the slip increases means the rotor speed must decrease. So this is a very beautiful concept. So by externally we are injecting the voltage into the rotor. So therefore if this injecting voltage is in phase with the original EMF induced in the rotor, the overall value of the induced EMF in the rotor will increase. So otherwise if you go for the opposition case, the total induced EMF in the rotor will decrease. And for a constant torque demand, if it is an addition process means the speed will increase. If it is subtraction process means the speed will decrease. I have already told this important concept. And now we will discuss one important concept which is called as the cascading or the tandem connection. So cascading or the tandem connection, it's a very important concept that you should always remember. It's a very beautiful concept. So cascading or tandem connection. Suppose there is this is a slip ring induction motor and this is a normal squirrel cage induction motor. Suppose if these two are connected, coupled together, then what is going to happen, that we are going to see here. Suppose the slip ring induction motor, we are going to give a supply. So we are going to give stator supply to the slip ring induction motor. As the rotor is a constant, so you can see clearly the rotor is same for both these induction motors. This is the slip ring induction motor and this is a squirrel cage induction motor. See, both having the same rotor. But here the slip ring induction motor, the rotor has winding. So we are going to take this winding terminals through the slip rings, and through the slip rings again we are going to give this winding to the stator of this squirrel cage induction motor. So this supply is going to give a supply. The rotor winding of this one is going to give supply to the stator of this squirrel cage induction motor. And now we will see what is the consequences of this one. So let me assume the supply frequency for the slip ring induction motor is F, and the number of poles on the stator is P1, and the synchronous speed of this rotating magnetic field in the slip ring induction motor is ns1, and the rotor speed is n1, and the slip is s1. Then the rotor frequency, or we can say the frequency which is induced in the rotor, is S times the supply. Here slip is S1, so S1 times the supply frequency F. This frequency is now giving us input to the stator of this squirrel cage induction motor. Let me assume the rotor is rotating at a speed of n2, and here the rotor is rotating at a speed of n1. So here the supply frequency is S1 into F, and the number of poles induced on the stator is P2. Then the synchronous speed of the rotating magnetic field is ns2, and the rotor speed is n2, and the slip of the squirrel cage induction motor is s2. But the rotor is same for both of this, so both should rotate at the same speed. So therefore n1 is equal to n2. So here n1 is for this slip ring induction motor. So n1 is equal to ns1 into 1 minus s1. This is for the slip ring induction motor. So n1 is equal to ns1 into 1 minus s1. So here ns1 is nothing but here 120 f by p1. So 120 f by p1 into 1 minus s1. This is the rotor speed with respect to slip ring induction motor. Then what is the rotor speed with respect to induction motor, which is here ns2 into 1 minus s2. So ns2 is nothing but 120. Here the supply frequency to the stator of this squirrel cage induction motor is s1 into f. So S1 into F by number of poles here, it is P2 into 1 minus S2. So both should be same. So we should equate these two terms. So now we have to equate the N1 is equal to N2. So we get when we assume S1 into S2 is nearly equal to 0. So when we assume S1 into S2 is nearly equal to 0, if you equate these two terms and after simplification we are going to get a complex term, and we are going to assume that S1 into S2 is nearly equal to 0. So S1 into S2 is nearly equal to 0. Then finally we are going to get S1, the slip of the slip ring induction motor, is equal to P2 by P1 plus P2, where P2 is the number of poles of the induction motor, squirrel cage induction motor, and P1 is the number of poles of the stator of the slip ring induction motor, which is S1 is equal to P2 by P1 plus P2. But what is the value of N1 is equal to N2 when cascaded in cumulative process? So therefore, where N1 is equal to N2. So N1 is equal to N2. So N1 is equal to N2 is equal to 120 F by. So N1 is equal to N2 is nothing but 120. So if you keep this S1, see, now I have already told you N1 is equal to NS1 into 1 minus S1. So therefore, here NS1 is equal to 120 F by P1 into 1 minus S1. So here N1 is equal to NS1 into 1 minus S1 is equal to 120 F by P1 into 1 minus S1. So in place of S1, substitute this term, and if you do the simplification, we are going to get N1 is equal to 120 F by P1 plus P2 is equal to N2, because both should be same. So this is the rotor speed, it is going to rotate. So 120 F1 by F by P1 plus P2. So 120 F by P1 plus P2, whenever we do the cascade is cumulative process. So cascade is cumulative process means the synchronous speed, the rotation of the synchronous speed in a slip ring induction motor and the induction motor is same. So whenever the rotation of the synchronous speed in the slip ring induction motor and the induction motor is in the same direction, then we can say when the cascade is cumulative process. Whenever the rotation of the synchronous speed in the slip ring induction motor and also in the induction motor, if both are in the same direction, then we can say the N1 is equal to N2 is equal to 120 F by P1 plus P2. It is said to be when cascade is cumulative process. So slip S1 is nothing but P2 by P1 plus P2, and N1 is equal to N2 is equal to 120 into F by P1 plus P2. Suppose when cascade is cumulative and P1 is greater than P2. So here, whenever the cascade is cumulative and P1 is very greater than P2, then what is going to happen? We are going to see here. See, I have already told you. See, let me assume P1 is greater than P2. Then what is NS1 is equal to? Here NS1 is equal to NS2 is equal to 120 F by P1, and N1 is equal to N2 is equal to 120 F by P1 plus P2. So whenever the P1 is greater than P2, we can say NS1 is equal to NS2 is equal to 120 F by P1, and N1 is equal to N2 is equal to 120 F by P1 plus P2. But whenever the cascade is whenever the cascade is differential, and again P1 is greater than P2, means NS1 is equal to NS2 is equal to 120 F by P2, and N1 is equal to N2 is equal to 120 F by magnitude of the P1 minus P2. So listen, whenever the cascade is cumulative and P1 is greater than P2, so P1 is greater than P2, so NS1 is equal to NS2 is equal to 120 F by P1, and N1 is equal to N2 is equal to 120 F by P1 plus P2. Whenever the cascade is differential and still P1 is greater than P2, so therefore NS1 is equal to NS2 is equal to 120 F by P2, and N1 is equal to N2 is equal to 120 F by P1 minus P2 magnitude of this one. So this is the 2 important formulas that you always have to remember for your lifetime. So whenever the cascade is cumulative, the cascade is cumulative, here P1 is greater than P2, so P1 is greater than P2. You have to take the poles in such a manner, P1 is greater than P2, so therefore NS1 is equal to NS2 is equal to 120 F by P1, and N1 is equal to N2 is equal to 120 F by P1 plus P2. When cascade is in differential, both are in opposite manner, means the synchronous speed in the slip ring induction motor and the synchronous speed in the both are rotating in the opposite direction, the synchronous speed, it is said to be a differential process. So P1 is greater than P2 means NS1 is equal to NS2 is equal to 120 F by P2, and N1 is equal to N2 is equal to 120 F by P1 minus P2 magnitude of this one. So these are the 2 important formulas that you always have to remember for your lifetime.